paragraph question in question 1 and 2, and all questions in geography are compulsory. Never leave a blank space. Try to answer all the questions. Now, let's start with your examples of your short objective questions. Now, what we have here, we have a synoptic weather map. Let's look at the first question. It says, the synoptic weather map above represents the season. Now you have two options, winter and summer. So this requires you to be able to interpret the map or the synoptic weather map. How do you tell that season on the map? How do you identify the season on the map? Now, when you're looking at this map here, dominantly, you have L, which indicates low pressure in the interior of the map. So what does that mean? It shows that the season here is summer. Why do you say it is summer? Remember, L is representing pressure. And remember, pressure and temperature are inversely proportional, or they are opposite. When temperature is high, the pressure is low. And when the temperatures are low, the pressure is high. So which means if this was a winter map scale, it will have an H in the interior. But this one is a summer synoptic weather map because you can see it has got an L in the interior. Now, here are the questions. The synoptic map above represent what season? The season that is represented there is summer because of the reasons that I gave, because of the letter L there. And you can also see the mid-latitude cyclone is further south. Remember, the mid-latitude cyclones or cold fronts are always there on the map. They will always be there. The only thing is that they are going to vary in their position. They will move further south. As you can see here, if this mid-latitude cyclone was to move from west to east like this, because it is driven by the westerlies, it will not touch the land because it is during summer. So the land will not have influence. So the question that usually comes in examination, they say, during which season do mid-latitude cyclones affect the weather? Or they ask, during which season do mid-latitude cyclones occur? You must know that the mid-latitude cyclones occur throughout the year. But when do they affect the weather of South Africa? They affect the weather of South Africa during winter because they move northwards during winter. So when they move northwards is when they are closer to the land. And then when they say which season, you don't say because of the presence of the mid-latitude cyclone. You say the mid-latitude cyclone is approaching. The mid-latitude cyclone is approaching. You can see the mid-latitude cyclone here. It is approaching the land, but here it is not approaching because it is summer. It is further. So the mid-latitude cyclone is further south. So during winter, you say the mid-latitude cyclone is approaching. Here it is further south. So it does not affect the weather. Let's go to our next question. It says the weather station model at X. Here is the weather station at X. Then they say it's in the cold sector or warm sector. So when you're looking at the area behind the cold front is called the cold sector. But this one over here is a warm front. So behind this area over here, this whole area behind the warm front is called the warm sector. Is the area behind the warm front. This will be a tip of the warm front. And again, what you should know about the warm front is that the warm front hardly ever or it never affects the weather of South Africa during summer or during winter. The warm front never affects the weather of South Africa. Why? Because it is always further south. So it is further south during winter. It is even further or furthest during summer. So it never affects. So it's a common examination question. They can ask you between these two fronts, which front never affects the weather of South Africa. You must know the front that never affects the weather of South Africa, it is the warm front. The reason that it is further south every time. Now, our next, the weather station model at X, we said it is in the warm sector. Why warm sector? Because it is found behind the warm front. Then the temperature in Lesotho will be mostly probably be high. Why will the temperature in Lesotho be high? here is our Lesotho here. Why will the temperatures be high? Because we said temperature and pressure are inversely proportional. And the letters that you see here, the L and H, are representing pressure. So when you see L, it shows low pressure. And low pressure is created because the air is warm and it is rising. So here, the temperatures here will be warm because you see the pressure being low. The area of constant pressure between two highs and two lows at W. So we're looking at this W here. We're looking at this W here. Then we say the pressure, the area of constant pressure between two highs and two lows here. This is what we call a saddle. The area between two constant pressure is called a saddle. So which means now you have your high pressure that side, you have your high pressure this side. The area between these two high pressure cells is called a saddle. And the pressure cell found at U is the U. The pressure found at U. So here is the pressure found at U. I believe you studied your high pressure cells. So you have this one over here. You have the other high pressure here. So what will be the pressure cell there? It is the South Atlantic because it is found in the Atlantic Ocean. And then the next question, the pressure reading at the cut-off low in Mozambique is HPA. What HPA? Is it 10, or is it 1008? So what do? You go there, you say this Mozambique, the isobar is not given. So it is given here. But what you should know is that the difference from one isobar, what is an isobar? Is a line that joins places with the same atmospheric pressure. So difference between one isobar to another is 4 millibars. So when you go there, you're going to say 10, 12 minus 4, then this one is going to become 1008. That's how you get to that 1008. And then you could do the same if they ask you what is the air pressure at any, okay, you can see here this is a low pressure and the pressure here is 1600 millibars. And then because this is a low pressure, it means when you move away, the pressure will increase. But this one is a high pressure, meaning that when you move away from U, the pressure will increase. When you move away from U, you're moving outwards, the pressure will increase because this is a center of higher pressure. So it's 1020, it will be 1024. So it will increase like that when you move away from high pressure. But you must know it will increase by 4 millibars or 4 hectopascals. So what is the correct answer there? Is 1008. The wind direction from U to X will most likely be in which direction? So this is the direction from U to X. From U to X, what is this direction? So it's an easy direction. It's a grade 10 content. It's simple a map direction. So the direction there will be to southeasterly direction. The direction is in the southeasterly direction. Okay, now let's go to the next short objective question. This is Eben Heath Island. These are the questions on Eben Heath Island. It says here, evapotranspiration is dash in the rural area because open spaces reflect dash energy out to space. So it means now evapotranspiration is it low or is it high? Is it solar or is it terrestrial? So you have to mix these ones. Now, what is the correct answer there? The evapotranspiration is higher in rural areas because open spaces reflect solar energy into outer spaces. And now, cities experience less wind circulation because, number one, remember tropical cyclones. Why do tropical cyclones die over the land? Because of high friction. So what do tall buildings do? Tall buildings reduce the wind speed. So the cities experience less wind circulation because of the tall building. So there is less wind circulation there. It is not because buildings have more glass. More glass will influence urban heat island. It is not because buildings are of darker materials. Darker material will also favor urban heat island, and therefore, because dark material absorb heat, and then buildings are built of concrete, it will also favor the development of urban heat island. So the only answer here that is going to influence the wind circulation will be tall buildings. All these other factors are factors that influence the development of urban heat island. Let's go to the next question. This is not a reason for the development of the heat island. Number one, we have artificial surface. No, artificial surface does contribute to that. Artificial source of heat does contribute to heat. Density of buildings, yes, it does contribute to urban heat island because it provides larger absorption area. So which one is incorrect is the slope aspect. It doesn't matter where the sun is coming from. It doesn't matter. Remember, slope aspect refers to the direction to which the slope is facing. So this is not a reason for the development of the heat island. It doesn't matter where the slope is facing to. So all these other factors favors. All these other factors favors the development of heat island. There's only one that does not favor the development of urban heat island, which is the slope aspect. And then they say the pressure gradient that exists between the rural area and the city is mainly because. Now, this is an important question because you speak of pressure gradient. So you need to define what is pressure gradient. Then HP minus LP is equals to PG. So what do I mean by that? I say high pressure minus low pressure is equals to pressure gradient. So which means now the pressure gradient that exists. So when speaking of the pressure gradient, we're referring to that there is high pressure somewhere and there is low pressure somewhere, and that results in pressure gradient. So pressure gradient simply means the difference between high pressure and low pressure. So they say the pressure gradient that exists between the rural area and the city is mainly because the first answer is there is high pressure in the city. Now you ask yourself, why will there be high pressure in the city? What is the difference between cities and rural areas? Cities are warmer. So because they are warmer, the air rises. Because the air is rising in the city, so it means there is no high pressure in the city. The pressure is lower. So this one is going to fall out because of low pressure in the rural area. Now you're saying, what creates low pressure? Low pressure is created by high temperatures. Now, are temperatures low in urban areas? No. Remember, we're talking about urban heat island. So when you define urban heat island, you're saying the warmer urban area than its surrounding rural areas. So which means now the rural areas must be cooler. So if the rural areas are cool, it means they cannot have low pressure. Because they are cool, the air is heavy, so the air is sinking. So this one cannot be the correct one. Now the next one says high pressure in the rural area. Now high pressure, what will create high pressure in the rural area is because the air is cooler, so the air is subsiding. So this is the correct one. Now this one says high temperature in rural area. No. Now why are rural areas not cooler? Because in rural areas there's less industrial activities. There's low building density, there is a lot of short buildings, there's natural surfaces, so the rural areas are cooler. So this one says high temperatures in rural areas, so this one is incorrect because rural areas have got lower temperatures because of the natural surfaces, because of open water masses, because of the trees that are absorbing heat. So rural areas are cooler. So because rural areas are cooler, they are going to have high pressure. Then the air will be blowing from rural areas to urban areas. So high pressure in rural areas and low pressure in urban areas. So the correct one here will be number C. Now, let's look at this other one. The dash is or are responsible for the reduced insolation in the city. So what is this statement telling us? That there is less insolation, there is less solar energy that is able to reach the city. So now, when you look up here, you can see a line there. You can see a line there of pollution dome. You can see the line that represents pollution dome. What is pollution dome, by the way? It is the polluted air in or around the city, but it is a concept. It is a concept you can define in any way. You can say a parcel of polluted air in the city. It can be defined in a number of ways. So the area responsible for the reduced insolation in the city, can it be pollution dome? Can it be tall buildings? Will tall buildings reduce insolation? How will they do that? Can the sun reduce insolation? The sun is the source of insolation. Can reflection be the source of reduced insolation? What will be the correct answer? The pollution dome. So this is the pollution dome. So the sun's rays are bouncing off the pollution dome, and therefore they reduce insolation in the city. And then the pollution dome expands during the day mainly. So what does it mean? It means now the shape of the pollution dome. The shape of the pollution dome during the day will be a little bit higher. The shape of pollution dome during the day, it will expand during the day and it will go lower during the night. So the question is, the pollution dome expands during the day mainly because of more human activities, cloud cover, heat islands, or evaporation. So why will temperatures be higher and make this pollution dome to go higher during the night, during the day? It is because of more human activities. The main cause of the dome in the diagram above. So this is the diagram above. What is the main cause of this pollution dome? Now we're looking at reflection, we're looking at air circulation, we're looking at ebb and flow, we're looking at solar radiation, we're looking at reflection, we're looking at infrared, we're looking at dome dust. So the main cause of the dome. So what is causing pollution? So pollution dome, remember we're talking about polluted air in the city. So of all these answers, what is pollution? Which one create pollution here? So the answer becomes dust. That's the main cause of pollution here. The dust is the one that is causing pollution here. Okay, let's move on to the next question. This is another short objective question. The climatic phenomenon represented by AB is the katabatic or moisture front. This is your line AB. What is this line AB? It is a moisture front. So moisture front, you need to define what is a moisture front. Is a line that separates warm, moist air from cold, dry air. So this is your warm, moist air from the Atlantic Ocean, and this is your cold, dry air from the South Atlantic Ocean. So this is your moisture front. The reason or the season represented in the figure is winter or summer. What is a line thunderstorm? What is the moisture front going to do? Is going to give us line thunderstorm. During which season do we receive line thunderstorm? Or during which season do we experience this heavy rainfall? We experience this heavy rainfall during summer. So the correct answer there will be summer. It says line AB indicates a ridge or a trough. Now you need to know the difference between a ridge and a trough. Now, what is this? This is a low pressure, and the low pressure is extended. So an extended low pressure, a trough is an extended low pressure. Low pressure is a trough. Once it is extended like this, it's called a trough. Now this one over here is a high pressure. So once the high pressure becomes longer like that, or it is extended like that, what do you call it? We call it a ridge. So now you know two concepts here. You know what is a ridge. A ridge is an extended high pressure, and you know what is a trough. A trough is an extended low pressure. So what is the correct one now? The line thunderstorm occur along the trough line. So this line thunderstorm, this moisture front here is a trough line, because the reason why we have clouds is because the air is rising, and the air will only rise when the temperatures are high. And then this is going to result in what you call trough line. This is a trough line, and it occurs during summer. And then the air mass at D is influenced by here is your D, is influenced by the warm Mozambique or cold Benguela current. It is influenced, okay, I think I skipped 1.1.4, I'm sorry. At C, there is cold and dry, warm air, cold and dry, or warm and moist. At C, here is your C. So this is Atlantic Ocean influenced by the cold Benguela current. So the air here is cold and dry. The air mass at D is influenced by the warm Mozambique current or cold Benguela current. This is grade 10 syllabus. So you know the ocean current on the east will be the warm Mozambique current. Air mass C. Air mass C. Here is the air mass at C. Undercuts or overrides. So undercuts meaning that it goes underneath, or override meaning that it goes on top. Air mass D along the AB, which is the moisture front. This line over here is called the moisture front. This trough line is called a moisture front. This trough line over here is your moisture front. So the question is, the air mass at C is going to undercut. Now you need to know the characteristics of this air mass. This air mass is cold and dry. So it's cold and dry, therefore it's denser. So what will be the answer there? The answer for this question will be, it is going to undercut. It's going to go beneath. It is going to go beneath because it is heavier. This one over here on the east is warmer, so it will override. It is the one that's going to go above. Now, the air at D originates from the South Atlantic or Indian Ocean. At D, is it South Atlantic or Indian Ocean? It comes from the Indian Ocean. And lastly, the common type of precipitation east of line AB will be advection or a thunderstorm. So on the east of moisture front, this is where you're going to get this line thunderstorm. This way you're going to get the line thunderstorm on the east of the moisture front. So the common type of precipitation east of the line AB will be line thunderstorm. And why? Why are we getting line thunderstorm on the east? Because on the east, the air is warmer. Because the air is warmer, it rises, and it rises rapidly. And because the air rises rapidly, it condenses. On the east, the air rises, it rises rapidly, and it rises higher, resulting in the development of cumulonimbus cloud, the CB clouds. And then what is the weather associated with cumulonimbus clouds? It is heavy rainfall and thunderstorm. Weather associated with cumulonimbus cloud is heavy rainfall and thunderstorm. So because the air on the east is going to rise rapidly, and after rising rapidly is going to rise even higher, is going to result in the clouds that have vertical extension. The clouds that have got vertical extension and that are heavily laden with moisture. They've got a lot of moisture, and then therefore it's going to result in the development of thunderstorms and heavy rainfall on the east of the moisture front. Now, let's look at the long questions here. The first long question that I want us to quickly look at is the tropical cyclone here. State one condition that are required for the development of tropical cyclone. Give two pieces of evidence from the sketch to indicate that the tropical cyclone is in the mature stage. Now, let's look at the first question. State one condition required for the development of tropical cyclone. So, what is it that tropical cyclones need? Tropical cyclones need the temperatures of 27 degrees and above, plus 27 degrees temperatures above, but it must not just be temperatures of 27 degrees and above. It must be ocean temperatures, because it doesn't matter what temperatures are, so long as they are not on the ocean or in the ocean, that will not favor the development of tropical cyclone. It must be surface water temperatures or ocean temperatures of 27 degrees and above, not just temperatures of 27 degrees and above. And number one. Number two, what do tropical cyclones need to develop before 27 degrees temperatures and above? They also need Coriolis force. They need Coriolis force, because Coriolis force is the one that results in the rotation of the winds. They need Coriolis force. And then they also need high level of evaporation. What is the importance of high level of evaporation? Is to create low pressure or create intensive low pressure, because the air is rising. Now the pressure is getting lower and lower. And then where will this tropical cyclone get their energy from? They will get their energy from latent heat. So those are the conditions that are necessary or that are required for the development of tropical cyclone. You said 27 degrees Celsius and above, but ocean temperatures of 27 degrees and above, they also require what? Tropical cyclones also require Coriolis force. Coriolis force. What is the importance of Coriolis force? Is for the air to be able to rotate or to spin. And then also it requires high level of evaporation. What is the importance of evaporation? Evaporation, remember, is going to result in low pressure or intense low pressure created on the surface. And again, this is the low pressure, that is the evaporation that will further result in the release of latent heat to the tropical cyclone as the energy source for the tropical cyclone. Because the tropical cyclone needs energy. And where does tropical cyclone get their energy from? From the latent heat. Give two pieces of evidence from the sketch to indicate that the tropical cyclone is in a mature stage. How do you tell that this tropical cyclone is in a mature stage? Number one, you can see it has got an eye. It is well developed here. You can see from the cross section. You can also see from the sketch here that it has got an eye. That's number one. Give pieces of evidence from the sketch to indicate that the tropical cyclone is in the mature stage. So you can see there is an eye there to indicate that it's in a mature stage. It's clearly visible there. It is clearly visible also in the cross section. What else can you see there? What else can you see there? You can see the pressure, which is below 1000. The pressure is below 1000. So the pressure in the center here is 970. Is 970. So the isobaric interval in this case, it is 2 millibars. In this case, the isobaric interval here is 2 millibars. So the pressure in the center there will be 970 millibars or hectopascal. So it's indicating that the tropical cyclone is in a mature stage. What is the evidence? This is the evidence. And then again, it is important that sometimes the examiner can ask you to draw a symbol to represent the eye of the tropical cyclone. You see, that is the eye of the tropical cyclone. That is the eye of the tropical cyclone. This is the symbol for the eye of the tropical cyclone. It must be represented like that. Give a reason. Okay, what influence will subsiding air at A have on the cloud cover in the eye? So if the air is subsiding here in the eye, what influence will the subsiding air at the eye have on the cloud cover in the eye? So what are the conditions in the eye of a tropical cyclone? Number one, the conditions is that there is clear skies. It's clear skies. Why do we have clear skies in the eye of a tropical cyclone? Because of the subsiding air. So subsiding air will not condense because subsiding air is heated adiabatically. So the adiabatic heating that we experience when we're talking about air, it will occur when we're talking about, number one, the bare winds. The berg winds, why are berg winds hot and dry? Berg winds are hot and dry because they are heated adiabatically, meaning that as the air descends, it is heated. So during the occurrence of berg winds, do we have clouds? We don't have clouds. So it's the same condition. That is the same condition with the eye of the tropical cyclone. In the eye of the tropical cyclone, the air is subsiding. So a subsiding air is heated, and because the air is heated, there is no condensation. So I'm bringing these two concepts together because now we are doing revision. We have already done berg winds. We know they are hot and dry winds. Why are they hot and dry? Because the air is subsiding. Now, what's happening with the subsiding air? The subsiding air is heated. So those conditions are the same in the eye of a tropical cyclone and also with the berg winds. The air is subsiding, and what is the behavior of subsiding air? It is heated. And now when the air is heated, there is no cloud formation because the air is not going to condense. The air will only condense when it rises. And rising air is going to cool. And then the cooling is the one that is going to result in condensation. But the subsiding results in heating. Rising results in cooling. So I hope you understand why we are going to have I hope you understand what will be the influence of subsiding air in the eye of the tropical cyclone. It's going to result in clear skies, and then other conditions that you are going to get in the tropical cyclone's eye is that there is no precipitation. You cannot expect precipitation without clouds. And then another condition that you'll get in the eye of a tropical cyclone is that it's going to be calm condition. The conditions will be calm in the eye because this is what we call the eye wall. These cumulonimbus clouds here, they form what we call the eye wall. Because of the eye wall, the strong winds cannot go through the eye. The strong winds cannot go through the eye. That is why one of the conditions is that it is calm or wind still. It is calm or wind still in the eye of the tropical cyclone is because of the strong cumulonimbus clouds or thick cumulonimbus clouds that stops the wind from blowing into the eye. So you know the conditions in the eye. You know it's clear skies. Why clear skies? Because the air is subsiding. Subsiding air will not condense. That is okay. I've already given the reason why we are going to have clear skies. We're going to have clear skies because the air is subsiding, and because the air is subsiding, the air is going to be heated, and when the air is heated, that air is not going to condense. That is why we don't have clouds in the eye of the tropical cyclone. Now, indicate the relationship between the wind speed and air pressure as indicated by the graph above. This is our graph above, and then this point over here will be at the eye of a tropical cyclone. Now, what are we looking at here? We're looking ahead of the eye, before this eye comes. So ahead of the eye will be at this point. Ahead of the eye will be at this point. So ahead of the eye, wind speed will be high and the air pressure will be low because you can see the air is rising there. You can see the air is rising there. It shows that there is it shows that the pressure is low here because the air is rising. So ahead of the eye, we are going to have high wind speed and we are going to have low pressure. And then within an eye, what's going to happen within an eye? Because the air is subsiding, it creates high pressure. And within the eye, because of these cumulonimbus clouds that stop the air from blowing in, we are going to have a very low wind speed. There is calm condition in the eye of the tropical cyclone. And now the next question, last question of the tropical cyclone says here, how does the leading or left quadrant dangerous semicircle develop in the tropical cyclone? The tropical cyclone is moving from east to west. Why does it move from east to west? It is driven by the tropical easterlies. Tropical cyclones are not driven by the easterlies. They are driven by the tropical easterlies. You cannot give an answer that says easterlies because number one, we have two sets of easterlies in our circulation. We have polar easterlies and tropical easterlies. So the answer has to be specific. It must be tropical easterlies. Now, this is the general direction of the storm from east to west because they are driven by tropical easterlies. And now when you're looking at the circulation of air here, it is also from east to west. The air circulation, remember this is a clockwise circulation. The air is circulating in a clockwise direction. So because of this clockwise circulation, at this point, the circulation is to the east. At this point, the circulation is to the east and the general direction is to the east. So that is how the dangerous semicircle develops. How does the leading or left quadrant dangerous semicircle develop? It develops when the general direction and the circulation direction are the same. The general direction from east to west and the circulation direction are also from east to west are the same. General direction are the same as circulation, east to west. So that is when the tropical cyclone is going to have that dangerous semicircle. So these are the answers that we spoke. Now we're looking at other source-based question. This is representation of the summer condition. Now, what is the question? The first question say identify one factor in sketch A that influences the weather of South Africa. So this is sketch A. So what is influencing the weather of South Africa here? It is South Atlantic, it is Kalahari high pressure, it is South Indian, it is cold Benguela current, it is warm Mozambique. That's not even a question. This was just a teaser. It's so easy. You just look at any of the factors here and you get a free mark here. And now next question. How would the position of the South Atlantic high pressure influence the moisture content of the air reaching the east coast of South Africa in summer? How would the position of the South Indian high pressure influence the moisture content of the air reaching the east? Now, the South, now what has happened now with the high pressure? The high pressures, remember we said they are following this high pressure cells, they are following the migration of the ITCZ. So when it is summer, they move further south, and then when it is winter, they move further north. They move in this direction. They move further south and north according to different seasons. And then Kalahari high pressure does not move south and north, it moves up and down. So it is higher during summer and it is lower during winter. This is Kalahari high pressure. It moves up and down. This one moves north and south. So the question is, how would the position of the South Indian high pressure influence the moisture content of the air reaching the east coast of South Africa in summer? So what does it mean now? It means during summer, the South Atlantic high pressure is further south and therefore is going to allow warm moist air to enter the interior. And this warm moist air in the interior will now condense because it's going to rise and cool. After condensing, it's going to result in the cloud, and the clouds will result in precipitation. So how would the position of the South Indian high pressure influence the moisture content of the air reaching the east coast of South Africa? What do you say in summer? Saying that because the South Indian high pressure is further south, it allows the warm moist air to go into the interior, and therefore it allows warm moist air to come into the interior. Why is the Kalahari high pressure weakly developed over the land in summer? This is your Kalahari high pressure. Now you can see the inversion layer is above the escarpment here. Why is this the case? It's because the Kalahari high pressure is higher in the atmosphere. And then why is Kalahari high pressure higher in the atmosphere? Because there is strong convection. there is strong convection. So there is a lot of rising warm air, convection or vertical movement of air. So the question says, why is the Kalahari high pressure weakly developed over the land in summer? It is because, number one, we have strong convection. There is more rising air. And now the question can be opposite. It can say, why is the Kalahari high pressure weaker or stronger during winter? Why is it stronger during winter? It is stronger during winter. So you can just change this and say, okay, here this one is saying weaker. You can change the question and say, put the opposite of that question, say, why is it stronger during winter? Then change summer to winter. Then it is stronger during winter because there is strong subsidence. There is strong subsidence. Remember now we're saying there is strong convection during summer, and during winter there will be strong subsidence. And then this during winter will mean now, because of strong subsidence, the inversion layer, this inversion layer will move below the escarpment, and trap warm moist air. So this one indicates a weaker Kalahari high pressure. This one will indicate a stronger Kalahari high pressure. So this is what will happen for different seasons. And this layer, remember, we call it the inversion layer. This layer is called inversion layer. It's called inversion layer because it is at the plateau. If it was in the valley, we will call it thermal belt, but it indicates temperature inversion, which the increase of temperature with height. The increase of temperature with height. So many times learners confuse the concept inversion layer and thermal belt. You only get the thermal belt. You only get the thermal belt in the valley. You get the thermal belt in the valley, but at the plateau, here you get inversion layer. Though they are same, they cannot be called with the same name. They cannot be called with the same name because even though they are both indicating the increase of temperature with height, which is temperature inversion. Temperature inversion is the increase of temperature with height. You will see here temperature inversion in the plateau here because of the weak and strong Kalahari high pressure. You'll also get that in the valley, but you cannot use the two concepts interchangeably. Inversion layer remains at the plateau and the thermal belt remains in the valley. That's how you should know them. Now, how does the weakly developed Kalahari high pressure cell influence the presence of the inversion layer in sketch B? How does the weakly developed Kalahari high pressure cell influence the presence of the inversion layer in sketch B? This is our sketch B. How does the weak inversion influence the presence? Weak Kalahari high pressure. Now, how does it influence it? The inversion layer is above the escarpment. So you can ask that question in opposite direction and say, how does the strong Kalahari high pressure influence the position of the inversion layer? You can say it goes below the escarpment. But for this question here, it says, how does the weakly developed Kalahari high pressure cell influence the presence of the inversion layer? Now you say the inversion layer is above the escarpment. So if you ask this question in opposite and you say, how does the strong developed Kalahari high pressure cell influence the presence of inversion layer in sketch, whatever sketch, or in winter, you say it goes below the escarpment. Okay, I am not going to just go through the questions that are asked here. I'm going to go through possible ways in which these questions can be asked so that you are better prepared for your paper. Now, the next question says, in a paragraph of approximately 8 lines, explain how the position of the inversion layer will bring overcast and unstable weather conditions. over the interior of the country in summer. In a paragraph of approximately 8 lines, now you are stated how long must the paragraph be. But we said the length is not so key to the to this question. What is more key to the question is that you must look at the allocation of marks. The question wants you to give 4 answers. So it says, explain how the position of the inversion layer will bring overcast and unstable weather conditions over the interior of the country in summer. So there is a weak subsidence of air over the plateau. There's going to be weak subsidence over the plateau, number 1, and the land is going to heat up excessively over the central interior. The warm moist air from the warm Mozambique current will reach from the South Indian up the escarpment, and the warm moist air will reach the interior of the country because the inversion layer is above the plateau. There is lots of cloud formation. There's going to be widespread of rainfall during summer. So in a paragraph of approximately 8 lines, how the position of the inversion layer. Okay, now it's very important that you are able to respond. It's very important that you are able to respond to this question for both summer and winter. What will happen during summer? The inversion layer is above the escarpment. Warm moist air goes into the interior. Warm moist air condenses cloud formation. Cloud formation is going to result in precipitation during summer. But during winter, the inversion layer is below the escarpment. And when the inversion layer is below the escarpment, warm moist air cannot go into the interior. If the warm moist air cannot go into the interior, there's no condensation. It's going to result in the stable conditions. But here we're talking about the unstable condition, indicating that the air is rising. But for winter, we're going to have stable conditions, meaning that the air is denser and it's sitting on the ground, it's not going anywhere. Now, let's quickly run to geomorphology. Let's quickly run to geomorphology questions and see what questions we have here. Okay, in introduction to geomorphology here, we simply have what we call a water cycle. You can see precipitation is there, and you must know how to define precipitation. And then vegetation, you have transpiration, you have surface runoff, you have infiltration. So infiltration is simply referring to the absorption of water by the surface. And that's your percolation of water there. And through flow is the flow of water beneath the surface. That's what you get there. And groundwater is the water found beneath the earth's surface. River discharge refers to the volume of water as it passes a specific point at a specific time. So this is just an icebreaker to our geomorphology here, this water cycle. Let's look at the questions here. High-lying area that separates 2 drainage basins is known as the watershed. Point where 2 or more streams meet is known as the confluence. So easily, if you're looking at 2 streams, your confluence will be this point here, where this point over here will be your confluence, because you have this stream that is flowing into this stream. So this point over here will be your confluence, because that's where 2 streams meet. So any point where 2 streams are meeting, that point is called a confluence. Okay, and then a watershed is high-lying area that separates 2 drainage basins. Here we have an interfluve. So what does an interfluve do? If you have a drainage basin like this, and a drainage basin with the streams. This is one drainage basin with streams. So between the streams within one drainage basin, this is what you're going to get, an interfluve. But if you have one drainage basin here and another drainage basin next to it there, so the 2 drainage basins are separated by the watershed. Point when 2 or streams meet, we already said that it is confluence. Point where the river enters the sea is known as the mouth. but you should not say mouth, just like you could not say elbow when you're talking about river capture. It is not elbow, but it is elbow of capture. And also here you must be very aware, it must be river mouth, because it's not just any mouth, it's a river mouth. And then the elbow of capture, the point where river join or river diverts headwaters of another water, of another river, or a stronger, more energetic river diverts headwaters of another less energetic river. That point is not called an elbow. It's called an elbow of capture. Just like here, this is not necessarily a simple mouth, it's a river mouth. The upper limit of groundwater now, where do we go here? We go to the upper limit of groundwater. So if you have water, groundwater here, so this part of groundwater here, this part of groundwater will be the part that is on top here, the top part of groundwater. This is what we now call water table. This top part of the saturated. So this top part over here, this is what you call water table. The top surface of groundwater is called water table. And now the process, okay, base flow. Let me quickly go to base flow. I didn't look at base flow here. So this is what we call base flow, when water is flowing beneath the earth surface. When the water is flowing beneath the earth surface, we call that base flow. And then runoff is when the water is flowing on the surface. Infiltration, the process whereby water seeps under the ground, or the process where water is absorbed by the surface, we call that infiltration. The area drained by a river and its tributary is called the drainage basin. And then what we call the river and its tributary, we call it the area drained by the river system. So you can say it a river and its tributary, or you can say river system. The area that's drained by the river system is called drainage basin. So the river and its tributaries, they are together called a river system. A river that originates in areas of high rainfall but flows through dry area is known as the exotic river. So what is an exotic river? Is a river that has got the source in the highest, in the upper course of that particular river. There's high rainfall. But as that river flows lower, it flows past a dry area or a semi-arid area. So when that river passes through that point, it is known as exotic river. Now let's quickly go through these short questions on drainage patterns. Tributaries join the main river at right angle. Which one has main river joining at right angle? So both of these A and B. So that question will be for both. So this, when you're naming this will be a trellis pattern, and this one will be rectangular pattern. So the rectangular pattern, tributaries join the main river at right angle. So it's got characteristics of both. So trellis pattern, the tributary join at right angle, and also with the rectangular pattern, the tributaries join at right angle. So both A and B will be correct here. There are right angle bends along the course of the main river. So this will refer to B. The pattern occurs in folded mountains. So this one will be A, which is trellis pattern, and then developed in areas where faults occur parallel to each other. So it will refer to the rectangular pattern. So when you're looking at the underlying rock for a rectangular pattern, you say it is found in the rocks that have got faults or jointed igneous rocks. This is your this one will be your B, where there are faults or there are joints. Develop in areas where the faults occur parallel to each other. So this one over here, so there's a fault parallel to each other here. This one over here will be your fall. So long as you see the word falls there, the falls are parallel to each other, that one will be B. Tributaries are short. So your tributaries here are your short tributaries here. So this will be your A, your trellis pattern. Tributaries often flow from gaps or ports, So if the tributaries are joining from gaps or ports, so it will form on this trellis pattern. Now let's go to the next question. Short objective questions. Short objective questions. Now let's look at this river profile. The longitudinal profile in a diagram represents, so this is telling you that this is a longitudinal profile. So now what is a longitudinal profile? It is a view of the river from this point that we call the source of the river, where the river originates, and the point where the river enters the sea, which is called the river mouth. So because you are looking at the river from that point to that point, we call it what? A longitudinal profile. Is the review of the river from the source to the mouth. We call it a longitudinal profile. So they're saying this longitudinal profile of the river represented here is graded or ungraded. Now we're looking at the characteristics of the river here. What is the correct answer there? It is ungraded. So why do we say this river is ungraded? Because it has got nick points. Because there's a nick point which is a waterfall there, and it is uneven. The river profile there is uneven, so it is ungraded. The river course indicated by X on the longitudinal profile is there at X, this point X here. What is it called? Is it upper or middle? So it is still upper course there. This will be the upper course of the river. Erosion is dominant erosion at X. So where is our X? This is our X. Because it is in the upper course, what type of erosion is dominant there? It is vertical erosion that is dominant in the upper course. And then why do we have dominant vertical erosion in the upper course? Because in the upper course, the gradient is steep, and therefore there's going to be vertical erosion. And then the sharp drop in gradient indicated at B on the diagram is known as A. So here there's a sharp change here in the gradient. It's called a what? A waterfall. So this is a definition of what we call a nick point. This is a definition of what we call a nick point. What is a nick point? Is when there is a sudden change in the gradient of the river. Where there is a sudden change in the gradient of the river. Now, 2.1.5, headward or vertical erosion may result in the removal of the temporary base level of erosion. Which one is that? Is headward erosion. After the removal of the temporary base level at B, the river profile will have what shape? After this temporary is being removed, now the river is going to be flowing here. What will be the shape? What will be the shape here? The shape there will be a convex. Not convex, I'm sorry. Convex will be bending outwards. So this one will be a concave. After the removal of the temporary base level. So after all this are removed, now the river will have a concave profile, and now it will change from being ungraded to being graded. It will change from being ungraded because it's going to have a concave profile, and once it is now concave, smooth concave profile, it is now going to change from being ungraded to be graded. So what do we mean when we say it is graded? It will be in a state of equilibrium. There's going to be equilibrium. Let me write it here. Equilibrium. What do you mean when you say it's going to be in a state of equilibrium? It means there's going to be a balance between erosion and deposition. Right now, in this stage, the question said the dominant erosion. So it means there is a dominant erosion in this. So the dominant process in this river is erosion. The dominant process in this river is erosion, especially in this part, because there are still obstacles, there are still weak points there. So the river is trying to remove them. But once this is removed, there is not going to be any dominant process. The river will be in a state of balance between erosion and deposition. And we say that the river is in equilibrium. And now, because it's in equilibrium, it's going to take a concave shape because the river will have been graded. Because the river will have been graded. Now, the flow is predominant on the slope of the river profile indicated as S. Now, what is the stage here at S? The stage at S here is called lower course. It's at the lower course because you can see this is where the river is joining the sea. And then you can see already here, the river is already winding. And as the river winds, that process is called meandering. The river is meandering there. And then it indicates that there's a lower course. And then what will be the dominant flow is predominant here. So this is what we call a laminar flow. This is what we call a laminar flow. And then that is when a river is flowing in sheets that are separate from each other. There's no mixing of water at this stage. The river is flowing on separate sheets. That's when we call that process a laminar flow. Why is the river flowing in that kind of form? Why do we have laminar flow? Because the gradient is, the riverbed is smooth. So because of the smooth riverbed, there are no turbulences. So the river is flowing very smooth here. But when you look at here, at Z here, this will be the type of flow that is called turbulent flow. And this kind of river flow will take place in the upper course where there are weak points and there are waterfalls, there are rapids. So at this stage, the river will flow in a turbulent flow. But at this stage where it is smooth, it's going to have a laminar flow. And how do you define that laminar flow? Is when the river is flowing in separate sheets. It flows in separate sheets that are not touching each other. So you can see there, you have the flow there, you have the flow. So it goes like that. So it's indicating that there is no disturbances to water. But at this stage, at Z, you can see the water is bouncing up and down. So there's high chances of this water layers mixing with each other because of the uneven gradient. And then it will happen in the upper course, but the laminar flow, you will get it in the lower course. Now, what we have here, we have drainage basins that have got different densities. The first question is explain the concept drainage density. So when talking of density, we're simply referring total length of streams divided by total length of streams divided by the area drained by those streams. So what evidence indicate that sketch A has higher drainage density? Why do we say A has higher density? There are many tributaries. There are many tributaries here. And then determine the stream order at X in the sketch A. So how do you determine that? You say this is 1 and 1. 1 and 1, they're going to make 2. This is 1 and 2, they're going to remain at 2. This is 1 and 1, they're going to make 2. So you have 1 and 2, it remains at 2. Then you have 2 and 2 is going to result in 3. So determining the stream order at X will be stream order number 3. So as we speak of this order, okay, we'll talk about that. Let's finish these questions. Explain the influence of gradient or slope on drainage density. How does the gradient influence density? Now, the gradient and density, they are, if the gradient is steep, there's going to be high surface runoff, and because of high surface runoff, the density is going to be high. But if the gradient is gentle, there's going to be more infiltration and less runoff, and therefore it's going to be low density. Now, if we're looking at sketch A and sketch B, where do we have a steeper gradient? We have steeper gradient at B. Why do we say steeper gradient at B? Because there are more tributaries, which means there is more water flowing than at A. At A, there is more water infiltrating. That is why we have lower drainage density at A, because of the gentle gradient. Remember, now we're looking at the factors that influence drainage density. Factors that influence drainage density. Here we are given one, which is gradient. We also have vegetation. So now, if we're looking at this, looking at vegetation, which area will have more vegetation? A will have more vegetation, because vegetation is going to result in more infiltration. More infiltration is going to result in low drainage density. Then at B, it means now we have low vegetation. At B, we have low vegetation. That is why there is more surface runoff. And another factor that will influence drainage density will be also type of precipitation. So what do we mean here? It means that at X, or here at A, the type of precipitation here is soft rain. So soft rain results in more infiltration and less runoff. But here at B, it is heavy rainfall. Therefore, it's going to result in more runoff, which results in higher density. Then you can also look at another factor. It will be soil moisture. Which of the two soils here, soil moisture, which of the two, at A or B, where do we have more soil moisture? At A, there is less soil moisture, which means the surface at A is dry. Because it is dry, more water infiltrates. But at B, it is saturated. Because it is saturated, it allows less water to infiltrate. So most of the water is going to flow on the surface. And another factor that we can look at that will change this density will be porosity and permeability. It will be porosity and permeability. So what's happening here? Porosity. What is porosity? It's pore spaces per unit area. So it means at A, there are more pore spaces. And if you can look at the type of surface at A, you can say at A, we have sand. And now because of sand, there is more infiltration and less runoff. And therefore, it resulted in A having a low drainage density. And at B, you can say we have clay soil here. You can say we have clay soil here. And here we have sand soil or sandy soil. So here we have clay soil. Because of clay soil, there's going to be low porosity. Because of low porosity, there's going to be low permeability. So porosity influences permeability. So clay soil is less porous and it is also less permeable. Because it is less permeable, then it's going to result in high infiltration. It's going to result in high runoff and less infiltration, and therefore is going to have higher drainage density. So those are some of the factors that are going to influence. So now porosity and permeability will also influence drainage density. So at A, the surface is highly porous and highly permeable, resulting in more infiltration and less runoff. But at B, the clay soil is less porous, or it has got less porosity, and therefore it is less permeable. That is why we have what? More runoff. How do you tell there's more runoff? Because the density is high. How do you tell that there's low density? How do you tell this area is high permeable? It's highly permeable because there is more water infiltrating and there's less water flowing. Okay, now let's move. We have looked at the factors that influence the drainage density. Now let's go into drainage pattern in sketch B. Drainage pattern in sketch B and sketch A are the same. The drainage pattern here is the same. It's different in terms of density. So the drainage pattern for A and B will be dendritic. How do you tell it is dendritic? Because it looks like the branches of a tree. It does not look like a tree. It looks like the branches of a tree. And then the tributaries join the mainstream at acute angle. Those are the characteristics of the dendritic pattern. And then those are the reasons. Identify the drainage pattern. We said, what is the pattern? Dendritic for both A and B. For both A and B. Because the difference between A and B is just density. But the shape is the same. It's dendritic pattern. So why do we say? Give a reason. Why do you say it's dendritic? Because it looks like the branches of the tree, and because again the tributaries join the mainstream at the acute angle. And then another reason that they can ask you, another question that they can ask you is to describe the underlying rock. Then you say the underlying rock here is the rock with similar resistance, the rock with similar resistance to erosion, or the rock with same resistance. But when you quickly go back to this one, you can say this one, the underlying rock is soft and hard rock following each other. Here we said, here what we have for this pattern, we have jointed igneous rock. We have jointed igneous rock or igneous rock with faults or cracks. Here is folded mountains, but here with this one, here this one we say is a surface with a uniform resistance to erosion. Okay, let's move on to the next one. One of the most common examination questions will be river capture or stream piracy together with river rejuvenation. Now let's quickly look at this river capture questions. What evidence in sketch X indicates that the river capture is likely to take place? So what do you do here? You look at sketch X. So you see here is headward erosion. So what is headward erosion? Headward erosion. Remember, this water is flowing and going in this direction. So as this water is going in this direction, now the water erosion is taking place in this direction. Backwards. So what is headward erosion? When the river erodes backwards, or when the river erodes towards the source. So it's eroding backwards. So what evidence in sketch X indicates that river capture is likely to take place? So what do? You look at here, you're saying headward erosion is taking place. Tributary of river A is cutting through the watershed. So this place over here is the watershed. So what is happening here? This tributary is cutting through the watershed. It is also important for you to know what do we call the process where the river is cutting through the watershed. That is called what you call abstraction. That process is called abstraction. So we have two processes here. We have one, headward erosion, where the river is eroding towards the source or backward, and abstraction is the lowering and the removal of the watershed, or is the retreat of the watershed. The lowering and the removal of the watershed is called abstraction. What could have caused the Captor stream to erode through the watershed? Why was this river able to cut through the watershed? Now, you need to know what are the factors that contribute to river rejuvenation. It's because what? It was flowing on a steeper gradient. It was flowing on a softer rock. Because of softer rock, it's going to be easily eroded. It is because of increased volume of water, because of increased rainfall. So this could be asked in a simple way: what are the causes of river capture? So one river must be flowing on a steeper gradient. It must also be flowing on a lower gradient. You can also add here, it is flowing on a lower gradient. It's on a lower lying area. It's also flowing on a lower lying area. Now, what's the next question? Identify features C and B of river capture in stage 1. So where is river C? This is the point here, river C, and this is this point here. This is river D. So identify feature C. So C is the elbow of capture. This is not an elbow, it's an elbow of capture. And it's D is a misfit stream. It's a misfit stream. And now the question it can ask you a question: what will happen to, or we can give characteristics of river D after river capture, or we can give the impacts of river capture on river D. So what will happen at D? River D will have less water. Because it has less water, there's going to be more deposition and less erosion. And then it can also be asked a question to give the impacts or the implication it will have. And also when you're looking at river E, look at river E. What has happened to river E? River E has got increased in what you can see that it is thicker in color now compared to this one. So it means it has gained more water. Explain the process that resulted in the formation of feature D. Explain the process that resulted in the formation of feature D. What is feature D? It's a misfit stream. How did the misfit stream form? How did the misfit stream form? Number one, headwaters of the misfit stream was cut off by the capture stream. So its headwater has been cut off. It continued to flow after the wind gap with reduced supply of water. So what has happened here is that this is the headwaters. Headwaters is the water that is flowing from the source. Now it has been diverted, it has taken another direction. So now this river has a shortage of water. Now, you can also give what will happen to the people that are living around here in terms of their activities. They're going to have less water for farming, less water for irrigation, for household. So those are type of questions that can be asked. It can be asked to give the impacts of this, the impacts to the people or the impacts on the river themselves. So when they say what are the impacts, the physical impact on the rivers themselves, this river is going to have shortage of water, but this river is going to have high volume of water. Now let's look at the final question here. It says, in a paragraph of approximately 8 lines, describe how the increased volume of water will positively impact on the farming community at E. So how will the farming community be impacted here? Now there's going to be more water for irrigation, which means now at D there's less water for irrigation. There's going to be more water for livestock, increased yields due to the abundance of water, decrease in cost to obtain sufficient water for irrigation, so they don't have to spend more money because water is readily available. Increased flooding increases natural fertilization of soil. Input cost to farm decreases, so there's going to be less money spent. Farming now is economically viable. More jobs are created as more areas are put under cultivation. Increase in income as farming yields increases. Increase in domestic water. Increase in nutritional activities. Food security is secure since there is more access to food, more water for aquaculture. So this is the impacts to people. The question can also be, what is the physical impact, or what is the impact on the river? So now what's going to happen to the river? The river is going to have increased volume of water. The river is going to flow faster, increase velocity. The river is going to increase its vertical erosion. Then there's going to be less deposition because river has got more energy, and its carrying capacity will also increase. So here this question was looking for the impact to the people around, or the impact to the people living closer to the river. So this impact can also be on the rivers themselves. So you must be careful. That question can be asked in a number of ways. And again, you should be able, so many times you make a mistake because you give the characteristics of river E at river D. You must know which one has gained water and which one has lost water. So it's very important that you are able to look at those. What you have there, you have fluvial landforms. Identify the fluvial landform at A and B respectively. So when you're looking at this one fluvial landform here, this is your braided stream, and when you're looking at this one here, because you can see there's an ocean here, so B will become a delta. Where in the river will one find the fluvial landform at B? This fluvial landform, which is the delta. Where do you find the delta? At the mouth of the river. Where in the river will you find this? You find it at the mouth of the river or in the lower course of the river. Explain how the fluvial landform A is formed. How is landform A formed? How is stream is formed in the lower course of the river? So what is happening there? As the river is flowing, it deposits the material on its own course. It's happened that there is deposition of sediments in the course of the river. Because it is in the lower course, the river is unable to cut through the deposit. So what does the river do? The river starts to wind around. The river starts to wind around the deposits. So when the river starts to flow or wind around the deposit, it's going to result in different channels or in number of channels, or the river is going to split in many channels. And as the river splits in many channels, this is going to result in the development of what we call braided streams. And then write a paragraph of not more than 8 lines and discuss the significance or the importance of fluvial landform at B. What is the fluvial landform at B? There's a number of importance of this, and now some of the factors, we can look at them as economic importance, you can look at them as social importance, and can also look at them as environmental importance. Let's look at the importance now of the deltas. They support biodiversity. It means now there's plants and animals that can be found there. It's a habitat for migratory birds that can be migrating from one place to another. They can live in the deltas. They are nursery grounds for marine life. They are natural barriers against storms and erosion. So because there's vegetation around the deltas, this vegetation will also reduce the wind speed. So it stops erosion and reduce the storm. So that's one of the reasons why the tropical cyclones will reduce their speed when they come through the land or over the land, because number one, they start with the friction from the deltas. And now, what will be the economic importance of deltas? Because of the fertile soil, it's good for agriculture. They also support fishing. They are also tourist attraction. The deltas can also be used for human settlements. They can also be used as historical and spiritual sites. People can go there to go and worship and do whatever their interest. And again, deltas are important for education and research. And you can see there, we are also talking about delta in our education system. So it means now it is also important for education and research. Now, let's quickly go through Mapwork activities. What are we going to look at here? So, we're going to look at gradient. So before you can know how to calculate gradient, you must know how height is represented on the map. Number one, height is represented through using of the contour lines. This the contour lines there on the map. Number 2, height is shown on the map through use of the trick station. What is important is the trick station. You must know trick station has got 2 numbers to it. It's got this full number or whole number 72. It represents that is trick station number 72. And also at the bottom, it's got a number that has got a decimal comma. It shows the height of that particular trick station. Height on the map can also be represented using spot heights. So this is your spot height. It's a spot plus a number. It's a dot and a number. So we call that a spot height. And then also we can use benchmark to represent height on the map. So this is a benchmark. You will usually find the benchmarks on the sides of the roads. Okay, now let's calculate vertical exaggeration first. The formula for vertical exaggeration is equals to vertical scale over horizontal scale. Vertical scale over horizontal scale. Now, your horizontal scale is always given. Your horizontal scale is always given. So when you calculate vertical exaggeration, you do vertical scale over horizontal scale, and you know your horizontal scale is always given on the map. But your vertical scale, what is your vertical scale? Your vertical scale is not given. You work out your vertical scale. How do you work your vertical scale? You look at your contour interval. And you must remember, your contour interval is always in meters. Your contour interval, height on the map is shown in meters. So your contour interval will also be in meters. Now, let's try to calculate, try to do a general calculation of vertical exaggeration. Now, if you calculate vertical exaggeration, now you have to know now your contour interval. You say now, how it is 20 meters. Your vertical scale is not given to you, but your horizontal scale is given to you. How do you work out your your vertical scale? You're saying now, because my vertical scale is not given, but what I know is that the vertical interval on the map is 20 meters, then what do you say? You say, how many centimeters are there? How many centimeters are there in a meter? How many centimeters are there in 1 meter? Then you say there are 100 centimeters in a meter. Then you say now, which means now you have to get 100 centimeters in each meter, and you multiply that by 20 meters. Then you're going to get 2,000. Vertical exaggeration. What is the formula for vertical exaggeration? Vertical exaggeration is equals to vertical scale over horizontal scale. I think we get that. Now, how do you calculate vertical exaggeration? You divide your vertical scale by your horizontal scale. What is your given horizontal scale? Your given horizontal scale for your topographical map is 1:50,000. And for your orthophoto is 1:10,000. In this case, we're going to use a vertical scale. We're going to use a horizontal scale of a topographical map, which is 1:50,000. So what do we do now? We say the horizontal scale is given is 1:50,000. Are we given any vertical scale? No, we are not given any vertical scale. But what information do we have? We know that our contour interval on the map is 20 meters. Now, how do we get our vertical scale? How do we get the vertical scale? You say, how many centimeters are there in a meter? There are 100 centimeters in a meter. But now our contour interval is not 1 meter. Our contour interval is 20 meters. Now we're saying 100 centimeters multiplied by 20 meters is equals to 2,000. It's going to be 2,000. Now we have worked out our vertical scale. What is our vertical scale? 1:2,000. Our horizontal scale was always given as 1:50,000. So we have to divide this. We say vertical exaggeration is equal to vertical scale over horizontal scale. So what do we do now? We're saying vertical scale. We say vertical scale, it is 1/50,000. 2000. It is 1 over 2000, and our horizontal scale is 1 over 50,000. 1 over 50,000. But now you cannot divide a fraction by a fraction. So instead, what do you do? You say 1 over 2000 multiplied by 50,000 over 1. So what do you do there? 50,000 times 1 is 50,000. Then 2,000 times 1 is equals to 2,000. So what do you get there? You say 50,000 divided by 2,000. So you do a simple, you simplify. So you cancel this 3 zeros by these 3 zeros. Then you have 50,000 divided by 2. So how many times does 2 goes into 50? It goes 25 times. So it means now on the topographical map, our vertical scale is exaggerated. The features on the topographical map will be exaggerated 25 times for them to be clearer. So our vertical exaggeration on the topographical map is done 25 times. So when you're looking at a feature on the topographical map, you are going to exaggerate it 25 times. Why do we do vertical exaggeration? To make the features to be clearer. So we're going to exaggerate it 25 times to make it clearer. Let's continue with our Mapwork. Here. So now, use the topographical map evidence. What has happened here? Okay. Now, use the topographical map evidence in your answer to the previous question and give 2 reasons why it will be difficult to construct a road. Okay, this one is it's a gradient calculations. This one is a gradient calculation. It's not a vertical exaggeration. So what are we looking at here? Contour lines in the topographical map is very close. So why is it going to be difficult for you to construct a road here? It is because the calculations here not calculation, sorry. It's because the contour lines will be closer to each other. Okay, let's move on. Let's look into our map interpretation. The dash in block E2 on the topographical map is an indication that seasonal rainfall occurs in the area. Now, you look at these things. Is it the row of trees? Is it perennial river? Is it a non-perennial river? Is it cultivated land? Now, what do we have there? You have cultivated lands there. Do you have any perennial river here? You don't have any perennial river. So what is the indication that will show that what will be the sign that indicate that the area receives seasonal rainfall here? It will be the non-perennial river. It is an indication that the area will receive periodic rainfall or seasonal rainfall. The non-perennial river. And then how is the non-perennial river represented? The non-perennial river is represented through the dots. It's represented through the river that is not flowing throughout. The river line is broken. But for the perennial river, the line is solid. Now, let's look at your map interpretation. Here is the question. Refer to the graph below indicating the average temperature of the area from H in block C1 to J in block C4 on the topographical map. Now let's look at the questions here. Identify the man-made feature that was responsible for the higher temperature recorded at X. So here is our point X. And now we have that. Why will the temperatures be higher? So what must you identify? You must identify man-made. Remember, in our previous slide, we're talking about the temperatures in urban areas and rural areas. Where are temperatures higher? Temperatures are higher in urban areas than in rural areas. Now, we must give the reason why are temperatures higher in urban areas. Number one, the tar roads, constructed buildings, these are the features that are going to make the temperatures to be higher in urban areas than in rural areas. And now, when you're looking at this rural area over here, what will make the temperatures to be cooler at this point? Why will temperatures be cooler at this point? Number one, you can see there's vegetation there. You can see there's a river there. So these are the natural features. So the question could be, what is the natural factor that are going to make the temperatures to be lower here? It is the natural vegetation here. It is also the river that are going to make the temperatures higher. Lower. And then what will be the factors that make the temperatures higher in urban area, in the build up? How do you see urban area on the map? You see the gray area is indicating the build up area. So also these are the type of roads that are also seen in the urban area. So the factors that are going to make temperatures to be higher here is built up area or constructed. The gray area is indicating this is a built up area, and also this is the tar roads that are going to make the urban areas to be warmer. But you're looking at the natural vegetation, and the rivers are going to make the rural areas cooler. And then because of that, this one will be cooler, and then pressure gradient will be created. So this will be high pressure and this will be low pressure, like in our previous slides. So air will be moving from rural areas to urban areas. So this is a typical example of what we spoke about when we're talking about urban heat island in the earlier slides when we're talking about temperatures. So temperatures will be lower here and will be higher here. So you can see here temperatures are lower, and as you go up, the temperatures are increasing. When you're moving from that point going there, this is your J, indicating the temperatures are lower. Why are temperatures lower here at J? You can see the graph here showing temperatures lower because you can see there's a river there, there's natural vegetation there. But when you go into H here, H is in urban area, so you can see now the graph is showing temperatures that has gone higher. Because of what? Because it's urban area with artificial surfaces that absorb heat, with roads that absorb heat, with more human activities. So urban heat island, when it comes to Mapwork, that should be the simple thing that you can do for yourself, because it's going to be easy for you to interpret it, because it is showing there on the map. So I expect everybody to get that. Why is temperatures low here and why is temperatures high here? So you have all those factors that makes temperatures to be high and low. And because of that, it's going to result in pressure gradient. Let's continue with our interpretation there. It's the same diagram that we are looking at. Now we're looking at the factors. Explain your answer to the previous question. So we have explained that we're identifying. So what were we doing here? We're simply identifying. So you will identify what are the features. Now, after you have identified the features, you have seen these features that makes temperatures to be low. The feature here is water. The feature here is vegetation. And then the feature here is road, and the feature here is also built up area. Now, we're taking it further. We're saying you're no longer identifying now. You're saying you explain now the answer. Why are these features making temperatures higher in urban areas, and why are these features making temperatures lower in rural areas. Now we're saying the tarred roads and buildings in the city town absorb heat and retain the heat, which will increase the temperature in this area, resulting in urban heat island. And then what will happen now in rural areas? Temperatures, natural surface are going to reflect, or trees are going to absorb. Here we're saying trees here are going to absorb heat, and you can say water masses are also going to moderate the temperatures. Now let's look at this other one. Okay, we have already done that. Now, another way of map interpretation can also be katabatic and anabatic winds. So if they say name the winds that will blow from A to B at night, the weight at night must tell you already that we are talking about valley winds. We know that we are talking about valley winds, and these valley winds must be during winter. So if they say during night or in the valley, you must know those winds. So long as you see the word night, you must know it is katabatic winds. And when they describe the nights these winds will blow, katabatic winds are going to develop during cold winter nights. It is going to be cold, calm winter nights. So there must not be winds. There must not be wind. It must be wind still. Because if the winds are blowing, it will not be clear. So this over here, you are going to have something like this. You're going to have something like this. So this is your katabatic winds. So during which season do they form? They form during cold winter nights. The first process that will take place will be terrestrial radiation, loss of heat by the surface. Then the cold air will go to the bottom of the valley, and it's going to force the warm air that was trapped in the bottom of the valley to move upslope. But the warm air will not move out of the valley. It will be trapped there in the middle of the valley, forming what we call thermal belt. Forming what we call thermal belt. My handwriting is a little bit terrible on a slippery surface. I'm writing on a very slippery. So that is called thermal belt. So what does this thermal belt show you? It shows you temperature inversion. And what's going to happen? More cold air is going to subside to the bottom of the valley. When more cold air subsides to the bottom of the valley, what's going to happen there? There's going to be frost pocket forming there. Frost pocket are going to form there in the middle of and at the bottom of the valley. So it will be during cold winter nights. And I think I came to the end of the revision for paper 1, and I would like to thank you for paying attention and for listening. Thank you. We shall see each other again when we do revision for paper 2. I thank you. Good day, learners.
the key concepts in regard with the question number 1. We're going to touch on the key concepts, the theory part, and also we relate it to the Mapwork part. So it's just a lecture to prepare you for the final examination when you're preparing for your question number 1 in paper 1, which is basically a question on climate and weather. Right. Without wasting time, we need to start with the background. We are going to look at the background, which is basically our grade 11 work. And this background is very important because it will help you to understand better the concepts that you're going to learn through the question of climate and weather. It's basically the background information, which is the basis of the understanding of the concepts under climate and weather. Right. So we are going to start with the high pressure cell and the low pressure cell. The difference between those two pressure cells. Right. And basically, we are going to differentiate between the two pressure cells in the southern hemisphere and in the northern hemisphere. Right. Because they are actually different according to the different hemispheres. Right. If we look at, we're looking at the first part here, we're looking at our high pressure cell. Our high pressure cell is actually what we call the anticyclone. The high pressure cell is what we refer to as the anticyclone. So it's basically an anticyclone, the high pressure cell. If we are to talk of it in another geographical perspective, we're talking of the high pressure cell as an anticyclone, like anticyclone like that. Right. And a low pressure cell, we are basically referring to it as a cyclonic cell. Right. So basically, when we're talking of cyclones, we're talking of low pressure cells. When we're talking of anticyclones, we're talking of high pressure cells. Right. We want to look at the difference between those two. Right. The first one is saying the air subsides. If you check at the bottom here, you see that the air is subsiding. Meaning to say, when we're having a high pressure cell, we have typically descending air. The air will be having a downward movement. If this is our ground, we are saying the air is coming from the upper atmosphere, is converging in the upper atmosphere. There's convergence here in the upper atmosphere, and the air is descending or is sinking. And as the air sinks, it's going to diverge in the lower atmosphere, which is our ground surface. So there's convergence in the upper atmosphere and there's divergence at the bottom here. That is basically the high pressure cell. And it says the air diverges at the center. We've talked about that. The air is diverging here, is going into different directions. It sinks, it meets in the upper atmosphere and it goes down. And as it goes down, it diverges in the lower atmosphere. We have clear or dry skies. That is typical of an anticyclone. When we're having anticyclonic conditions, we have clear conditions. We do have clear skies, or we have dry skies. Why do we have dry skies? It's because the air is sinking. For us to have unstable conditions, we need air which is uplifting. But in this instance, the air is actually going the opposite direction. The air is sinking, which will result in dry skies or clear skies, or what we call the stable conditions. Right. And there's also no release of latent heat and no cloud formation. Yes, we cannot have clouds forming. Clouds need to form when we have upliftment of air, of warm and moist air. Then the air circulates in an anti-clockwise rotation. Right. If you are looking at our high pressure cell in the southern hemisphere, the air moves out of the high pressure cell, not in a straight motion, but it circulates. And the circulation is anti-clockwise, like what you are seeing here. It's anti-clockwise against the direction of the clock. The clock, remember, is 12 there, and it's 6, and is 3, and is 9. The clock moves in this direction from 12 to 3 to 6 to 9. But if it's anti-clockwise, it means it's going against the direction of movement of the clock. So it's anti-clockwise rotation. So the air, as the air is actually coming out of the high pressure cell, as it diverges on the lower atmosphere, it diverges in an anti-clockwise circulation. Then we also have the isobar values increase towards the center of the high pressure. Right. If we check here, the center of the high will be the mid of our high pressure cell. Like if you can check here, you tend to find that this is actually the center of the high pressure cell. We're having the center here, which will mean that we have a higher value here. Like if you can see what you're seeing, we have 1035 hectopascals and we have 1030, which means our isobar values are going to decrease as we go out of the cell. The highest figure should be at the center of the high pressure cell, and they will decrease going outwards. And also you need to note the isobar interval, the difference in pressure between two next isobars next to each other. Like if you can check here, our isobar interval is 5 hectopascals. The first one at the mid of the high pressure cell is 1035, like this one that we are seeing here. And the next one is 1030, meaning to say our interval there is 5 hectopascals, which means the pressure is changing or is indicated in intervals of 5. Right. And you also, it's called anticyclones. We've talked about that. And we have typical 3 subtropical anticyclones that affect the weather system in South Africa. We have on the west, we have the South Atlantic, and we have on the east, the South Indian, and also we have over the interior, we have the Kalahari anticyclone or the Kalahari high pressure cell. Those are the 3 typical anticyclones that affect South African weather. So we basically have on the west, the South Atlantic, on the east, the South Indian, and over the interior, we do have the Kalahari high pressure cell or Kalahari anticyclone. Right, then we quickly go to the low pressure cells, which are the cyclonic conditions. Right, here is now basically the opposite. We have said that the high pressure cell is an anticyclone. Now the low pressure cell is a cyclone. It's a cyclonic system. And how does it operate? If you are to check on the low pressure cell, right, the low pressure cell, you can see that typically at the center of the cell, we have the lowest pressure occurring there. Like if you can check what we have at the mid of this system here, we have 1000 at the middle here, which is lower than what you are having on the outer part of the system. This is 1000, this is 1005, meaning to say our pressure is lowest at the center of the system, which is the opposite of what's happening here. The pressure was highest, the atmospheric pressure was highest at the center, but now it's lower, and our isobars value are increasing as we go out of the system. As we move out of the center of the system, from the center of the system, our pressure is increasing. The atmospheric pressure is increasing as we go out of the system. So that is typically a low pressure cell. So we have air ascending. Ascending, we are saying we have air which is uplifting like this. The air now is acting opposite of the high pressure cell. There's convergence at the bottom, assuming this is our ground. The air comes from high pressure and it converges. As it converges, it rises. And as it rises, it diverges in upper atmosphere. So there's divergence there in the upper atmosphere and there's convergence at the bottom. So that is basically the difference. And given this condition, we are most likely to have unstable conditions. We have cloud formation. Like if you are saying this is warm and moist air, which is converging and which is ultimately being forced to rise, it will ultimately get to the dew point level. It will condense, it will create clouds that are going to produce rainfall. So typically we have unstable conditions when we have a low pressure cell. It creates unstable condition. Condensation will take place because of the upliftment of the air. The air now is going upwards, is going into upper atmosphere, is going to reach at the dew point level, is going to condense, and is going to form clouds that will apparently bring precipitation. that is basically with a low pressure cell. And then latent heat is released during condensation. We have the release of latent heat, yes, as the condensation takes place, right? And also clouds form and precipitation occur. We talked about that. Then circular shaped isobars. Yes, they are circular shaped. You can see in this instance, the isobars are circular shaped. And we also have the air circulating now is a clockwise rotation. Take note of this. It's clockwise. When you are having an clockwise, but when you are having a low pressure cell, we have a clockwise rotation. So that is basically the difference of a high pressure cell and a low pressure cell. The circulation out of the high pressure cell is anti-clockwise, but the circulation into the low pressure cell as the air is feeding into the center of the low, it will be circulating in a clockwise direction. We are talking of typical of the southern hemisphere in this instance, because the circulation is not the same. It's the opposite in the two different hemispheres. If you are to look at the northern hemisphere, the circulation into the low is anti-clockwise. Circulation of air into the low pressure cell in the northern hemisphere is anti-clockwise. It's the opposite of what happens in the southern hemisphere. But basically for our studies, we are more focused on our southern hemisphere, since our questions are typically related to our typical climatic conditions in the south. So the circulation into the low pressure cell is basically a clockwise rotation. Then it's also known as a cyclone. We've talked about that. Isobar value decrease towards the center. We've talked about that. Then which typical low pressure cells do we have geographically? We have the coastal low. The coastal low, when we're talking of the coast, we are looking at the boundary of the waterboard and land. Coastal areas are those areas that are bound to the sea, those harbor places. Like you can talk of Durban, you can talk of Port Elizabeth, you can talk of those places which are just by the seaside. So we do have a typical low pressure which exists along those typical lines along the boundary of land and water. That is basically what we call the coastal low. And we are going to look at them when we do the backquins. When we're looking at the backquins, we are going to have a look at the coastal lows, because they are the ones that influence the occurrence of the backwinds. Right. Then we also have what we call the mid-latitude cyclones. Is typical of the first part of our study in climate and weather, which is also a question that you should take note of. Is a typical weather system that exists and that affects mainly the western part of South Africa, the western coast of South Africa, typically in winter, bringing in heavy rainfall and very cold conditions over the Western Cape in around Cape Town. The mid-latitude cyclone, we're going to talk of it. Then we also have the tropical cyclones, typical of weather systems that do affect the Southern African subcontinent, affecting mainly Madagascar, affecting Mozambique, affecting Zimbabwe into South Africa. Yes, it's typical of a weather system which is prevalent in late summer. We're going to look at it as we focus on it as a particular aspect of the study of climate. Right. So basically, we are looking at these concepts as background information. We need this background because it is going to be very useful, and we're going to use it as we go through the study of climate and weather. This is basically the background, and this is grade 11 work. You must be having this, and you must have it at your disposal of the fingertips. You must be knowing these things because they will apparently be very useful in your study of weather and climate as a particular topic, or also as a question in paper 1, question number 1. You must be very aware of the basic concepts of climate and weather. Then we also have to look at maybe the pressure belts. On the pressure belts, we don't need to waste much time. We just want to go through them, and they will also help us understand the formation of mid-latitude cyclones, and they will also help us understand tropical cyclones, because they are the basics of the study of those typical weather systems of the mid-latitude cyclone and also of the tropical cyclones. Right, we're now looking at our pressure belts. We are going to look at the pressure belts as fast as is possible. Right, if we check here, this is the polar region at 90 degrees south, and this is the polar region at 90 degrees north. We do have high pressure cells there. There is descending air, like what we have talked previously. When we have typical descending air, we do have a high pressure cell forming or an anticyclone forming. So at 90 degrees south, we have a high pressure cell, and at 90 degrees north, also we have a high pressure cell. There is descending air in those regions. Right. Then we go to the subpolar region, which is around 60 degrees to the north and around 60 to the south. In that pressure belt, we have a low pressure. That is typical of a belt which has got low pressure. It's called the subpolar low pressure belt. Right. Then we move on to the next pressure belt, which is around the region of 30 to the north and around the region of 30 degrees to the south. That is what we call the subtropical high pressure belt. It's subtropical high pressure in the north and subtropical high in the south. And South Africa actually falls within the subtropical high pressure south. It's dominantly in the subtropical high pressure south. Like if you check the latitude of South Africa, we do have latitudes ranging from around 23 degrees and 23 and a half in Limpopo, the Capricorn. And as we go down, we do have around 30, 34 going down to Cape Town, which means South Africa is basically falling around this subtropical high pressure belt. Right. And we have the equatorial low, which we call the ITCZ, the Intertropical Convergence Zone. This is typical of the mid position of our latitude values at 0 degrees. It is starting from 0, increasing, going to the north to 90, from 0 to 90, going to the north, and from 0 to 90, going to the south. And the central position is the equatorial low, which is at 0 degrees. And that belt is typically a low pressure belt. Because of intense heating, we have the sun being overhead across the whole year, and typically we have a low pressure cell developing because of intense heating. The air is always uplifting, there's convergence and there's upliftment, or the air will be ascending in that particular belt, and it will create unstable conditions and very high amounts of rainfall or precipitation in that particular belt. So those are the pressure belts that we have. So if you are to summarize it, start from the equator, start from the ITCZ, it's low, then it changes to high, it goes to low, and it goes to high. That's the sequence going to the north, and the same sequence applies as you go to the south. It's low at the equator, it's high at the subtropical, and it's low at the subpolar, and it's high as you go to the polar south. That is the sequence of the pressure belts. Then we go to circulation cells. And also the main problem that we usually have is learners that confuse between a pressure belt and a circulation cell. Those two are not the same. We do have 4 distinct pressure belts. The low pressure equatorial, the high pressure subtropical, the low pressure subpolar, and the high pressure polar. Those are the pressure belts that we have. Typically, we have 3 pressure belts. So if you get a question which asks about pressure belts, indicate the position and indicate the nature of the pressure. It's equatorial, meaning to say it's occurring around the equator. And what kind of pressure is it? It's a low pressure. So it's equatorial low. Then if you go to the next pressure belt, it's subtropical. And what kind of pressure is it? It's high. So it's subtropical high pressure. Then you go to the next belt. It's within the subpolar. It's not in the polar, it's the sub at 60 degrees to the north and to the south. It's subpolar high. So when you are naming those pressure belts, you have to indicate the location and you have to indicate the nature of the pressure in the belt. Do not just say it's polar. Do not just say subpolar or it's polar or subtropical. Then what kind of pressure is there? It's subtropical high, it's equatorial low, it's subpolar low, it's polar high. That is a complete description of a pressure belt. Then now let's quickly go through the circulation cells. Because of these pressure systems, we are going to look at the effect of Coriolis force as we go through the discussion. But for now, we just want to focus on maybe pressure gradient and look at the circulation cells. Because of the existence of differences in pressure between two pressure belts, if we have a high pressure cell and we have a low pressure cell, it will definitely mean that geographically there is pressure gradient. There is a difference in the levels of pressure, which will prompt the air to move from one region going to the other, because now there is a gradient. There is a difference in the pressure. Whenever we have a high pressure region and we have a low pressure somewhere, it will mean that the air has to blow from the high pressure going towards a region with lower concentration of air, which will be a lower pressure region. So because of that, it will create a sequence or a circulation that is going to exist. And it is going to create for us three typical circulation cells. Right. If we check here, we have a circulation cell which is happening here. The air is coming from the polar high, is going to the subpolar low, and is ascending, is feeding back, is going in that direction towards the closer to the Earth's surface. And as it gets there, the low subpolar, it rises and it feeds back to the high pressure cell. So at the end, it creates what we call a circulation cell. So typically we are saying there is circulation which is happening between the polar high and the subpolar low. Then if you also check here, there is another circulation happening. There is high pressure in the subtropical region here, if you can see, which means the air has to come from high going towards low subpolar, and is going to converge to meet with air coming from the polar high at the subpolar low region, and is going to ascend. Like we said, when there's convergence, the air is going to uplift, which will result in another circulation cell developing, like what you are seeing here. There is another circulation cell which is going to develop. And as you also check here, we also have another circulation cell which is occurring between the polar, between the subtropical high and the equatorial low. Because there's low pressure here, the air has to come from high pressure subtropical here. There is high pressure. The air is going to flow from high going to low, and is going again to converge from the air coming from subtropical south going to the equatorial low. It's going to meet there, converge, and also uplift and create another circulation cell. This is the circulation cell, and we also have another circulation cell happening there. So we are looking at those three circulation cells which do exist as a result of the differences in pressure along the different climatic regions and different pressure belts. So naming those cells, this is basically the same. If you have a question which is asking on the circulation cells, be aware of the three circulation cells that we have noted there, because it's basically the same. They might transpose them differently. This is on a globe like our Earth. You know, the shape of our Earth is spherical, and they might transpose them to a flat landscape. You have not to, I don't need to confuse yourself with that. It's still the same. We are just taking a perspective of the flat landscape, like what is happening here. What you are seeing here, these three circulation cells are the same cells that we have been talking about on the globe. So the North Pole, you can see that is indicated that is North Pole here, meaning to say we have 90 degrees to the north here, and we have our 60 degrees to the north and 30 degrees, and we have our equator, which will mean that this is 0 degrees, this is subtropical high, this is subpolar low, and this is polar high, though on a flat landscape. But basically, it's the same thing. So the circulation cell that we have from the equator, between the equator and the subtropical high, is called a Hadley cell. This one here is a Hadley cell. The first circulation cell, which is created by the circulation from the equator, from the subtropical high to the equator, the air rises as it reaches the equator or the ITCZ. It converges, it rises, it creates unstable conditions over the equator, and it sinks back in the subtropical region, which creates a high pressure around 30 degrees to the north and to the south. Then again, we have another circulation cell between the subtropical high and the subpolar low. Because there is pressure gradient, there is high pressure in the subtropical high and there is low pressure in the subpolar low, we have air moving in that particular direction, and it's going to converge with air coming from the polar high. And it's going to create another circulation cell, which we call the Ferrel cell. It's cell number 2. It's hardly from the equator to 30, subtropical high, north and south. Then from subtropical high, that is 30 degrees, around 30 degrees to the north and to the south, we go to 60, which is the subpolar. We have a Ferrel cell. Then lastly, between the polar region and the subpolar region, we do have what we call the polar cell, like what you are seeing here. It's called the polar cell. So those are the three basic circulation cells that are created because of the existence or the prevalence of the different pressure belts on a global scale, or because of the distribution of the different pressure cells on a global scale. So we do have those three circulation cells. So when you get a question which is asking about the circulation cells, do not confuse circulation cell to pressure belt. Pressure is either high or low. And where is it? Mention the region and indicate the nature of the pressure. That is a pressure belt. Circulation cells, there are basically three. We have the three basic circulation cells, which is the Hadley cell, the Ferrel cell, and the polar cell. Right. Then we go to Coriolis effect. We need also to encompass Coriolis effect. It's very critical and we need to understand it, and it is going to help us understand when we discuss the weather systems like the mid-latitude cyclones and also the tropical cyclones. Right. Coriolis force, this is the force which is created by the rotation of the Earth. Remember, the Earth is not stationary. The Earth is rotating. It's giving us days and nights. And it's giving us cycles of seasons and years because it's rotating. We have rotation and revolution. I think that is basic knowledge. You must be having that. We have rotation and revolution, which means the Earth is not stationary, it's also moving. So we are saying the air is moving from high pressure to low pressure because of pressure gradient. But however, the air is not going to move, or is not going to move according to our assumption of pressure gradient. Right, what am I saying here? We have if you have a high pressure cell here, there is high pressure around this region and there is low pressure there. It means there is pressure gradient between these two cells. There is a difference in pressure, which will definitely make the air flow from high going to low. It must attain a natural balance between those two pressure cells. There is high concentration of air molecules here, and there's low concentration here, which will prompt the air to move from the high to go to the lower. But however, there is also an effect of the rotation of the Earth. The Earth is also rotating, which will mean that the air, instead of it going straight from high to low, it has to be twisted in a direction because of the Earth, which is also moving. We are having a body of air which is moving over a moving body. So at the end, we do have a deflection, which we call the Coriolis effect. It will cause a deflection. Like the air will not move as according to pressure gradient like this, straight from high to low. It will not feed straight to the low, but however, it's going to be twisted in a given direction because of Coriolis effect. And this effect now, we need to note it clearly, how it affects the air in the south and how it affects the air in the north. And also, it is going to lead us to understand the planetary winds, what we call the planetary winds. For us to understand that they are based on Coriolis effect. Right. The deflection is to the left in the southern hemisphere. The air is going to be twisted to the left direction in the southern hemisphere, and the deflection in the northern hemisphere is to the right. You must note this. It's right in the northern hemisphere and it's left on the southern hemisphere. Let's go back to our illustration and see how that deflection will lead us to having different setup of planetary winds on a global scale. Right. We'll quickly go through our illustration of the globe, and we want to summarize the planetary winds that we have on a global scale as on the world Earth. Right. We have basically three different planetary sets of winds on a global scale. Right. Let's go to our illustration. Because we said deflection is to the left in the southern hemisphere and to the right in the northern hemisphere, which will mean that I will use this illustration here to indicate the deflective direction and also to indicate the nature of the planetary winds that we tend to happen in a different, in a particular geographical region. Right. We are saying here, we do have this belt. It's a high pressure belt. This is the polar high, around 90 degrees to the south. This is high pressure. And this is the subpolar. It's a low pressure. And this is a subtropical. It's a high pressure. And this one is a equatorial, or the ITCZ, which is the low pressure. The same sequence applies as we go to the north. It's low from the equator. It gets to high pressure in the subtropical. It goes to low pressure. It goes to high pressure at the end. So because of this, we tend to have air moving from high going to low. And also coming from high, it must go to low. Come from high, must go to low. From high, must go to low. But we are saying there is an effect of deflection, which is caused by Coriolis, which will tend to bend the air in a particular direction because of the rotational effect of the Earth. And we said our rotation is to the left in the southern hemisphere, which will imply that instead of this air going straight to low here, it is going to bend in that direction, leftwards. It's coming from high, going to low, but it's not going straight. It has to bend in that particular direction because of Coriolis effect. Then this one is coming from high, going to low, because the Coriolis effect is also going to twist in that direction. And this is leftward movement. Do not confuse yourself, because these two air masses are seeming like going to different directions. They are still going to the left. They are still deflecting to the left. It's left going that direction if you're coming from south to the north. And if you're coming from the north to the south, it's still left again. Your left direction is not the same if you are moving from different orientations. If you're coming from the south going to the north, your left is on the other side. If you're coming from the north going to the south, your left is on the other side, which will mean that this is leftward deflection and this is also leftward deflection. And lastly, there is high pressure at the polar region here, and there is subpolar low, which means the air must move from high polar to the subpolar low, and is also forced to deflect to the left. So this is going to create a belt of winds which has got this particular name according to the direction of flow of the air. Right. Geographically, let's go back. Geographically, we name winds according to their direction of flow. We name winds according to where they are coming from. That is how we name winds geographically. If we look at our indicator of wind direction, the wind vane, it points towards the direction of where the wind is coming from. So geographically, we also name winds according to the direction from which the winds are coming from. So if we check on our globe, this is the western part of our globe, and this is the eastern part of our globe. Remember, it's always west to the left and east to the right. And if we check these winds, they are starting from the eastern direction, they are going to the west. And where are they coming from? They're coming from the polar region here, and they are going in that direction. So this belt here is the belt of what we call the polar easterlies. They're coming from the east and they're originating from the polar region. They're called the polar easterlies. That is the belt of the polar easterlies. Then between this belt and this belt here, we are seeing that the winds are going in that direction. They are coming from the west, going to the east. This belt is the belt of what we call the westerlies. And in this belt here, they are going in that direction. You can see they are coming from the east and they're going to the west. This is a belt of the winds which we call the trade winds or the tropical easterlies. It's tropical easterlies. They're coming from the east going to the west, and they are in the tropical region, or we call them the trade winds. Those are our typical planetary winds on a global scale. So basically, that is the basis of the understanding of the weather systems and the climate and the weather are part of paper 1 question number 1. So relating it to practical geography, which is Mapwork, when you get typical questions asking about South African weather conditions, you must know that South Africa geographically is situated within the range of the subtropical high. That is why we have a limited amount of precipitation, because we are typically having stronger descending air. We are in a subtropical high pressure belt. So you need to actually figure out and relate to the belt in which South Africa lies geographically. South Africa typically lies within the subtropical belt. That is why we do not have as much rainfall, and also the rainfall is seasonal, typically because of the location of the basic location of the country according to the distribution of pressure cells. Right, let's quickly go to mid-latitude cyclones. That is the first part of climate and weather, the first part of the question, or question number 1. You are typically going to get questions on mid-latitude cyclones. Right, I'll quickly go through the basics of mid-latitude cyclones. We don't want to spend much time. We want to look at, we talked about cyclones. We said cyclones are basically low pressure weather systems. So when we're talking of mid-latitude cyclones, we already have an idea of what kind of weather systems are they. They are typical of low pressure weather systems. But where are they prevalent? In the mid-latitude. What is the latitude range of values? We have our latitudinal values stretching from 0 degrees at the equator, and they will end at 90 degrees in the north, and they will also end at 90 degrees in the south. So where is the mid position of the range of values of 0 degrees to 90 degrees? The mid position we are saying is around somewhere 45, 50. So we are looking at typical low pressure weather systems that do exist around the mid values of our distribution of the latitudinal values from 0 to 90. So if you can check on the globe here, we do have the mid-latitude region. This is our equator, and we do have the mid-latitude region indicated in the south and also indicated in the north. And what you should also note is we also have other namings of the same weather system. Usually that is a typical question that you can get in the examination. Give another name for the mid-latitude cyclone. Typically, that is a common name that we use for the weather system. We call them mid-latitude cyclones, but you might get a question which requires you to identify another name for the same weather system. They are also called moderate cyclone, or they are also called extratropical cyclone, or they are also called temperate cyclones, or frontal depressions. These are typical names of the same weather system. So if you find a question which requires you to give another name or an alternative name for a mid-latitude cyclone, always remember that they are having other names like the moderate cyclone, the extratropical, the temperate, or the frontal depression. Those are other alternative names for the same weather system, the mid-latitude cyclone. Right, let's go to the developmental stages. We can also get a question which requires you to identify a developmental stage of the weather system. This system, it goes through a number of developmental stages, which are basically 4 stages. Right. We have the initial stage, the first formative stage of the weather system. Right. What you should note here is that this weather system occurs around or along the polar front. And if you're talking of a front, I am sure geographically, we know what a front is. A front basically is a boundary which splits two air masses of different characteristics. What are the characteristics that we're talking about? Air masses can be different in terms of temperature. One might be cold, the other one might be warm. Those two air masses, they cannot mix. They will be split. There will be a boundary which is going to develop between them because of their differences in the properties. One is cold, one is warm. Those are two different characteristics. So those two air masses cannot effectively mix. Then they can also be different in terms of stability. One is sinking, it's creating stable conditions. One is rising, it's creating unstable conditions. So they cannot mix. Or they can also be different in terms of their moisture content. One can be dry and the other one can be moist. Those two air masses are different. So they will be split. There will be a boundary which will exist between them. That is what we call a front. So typically, if we check on a global scale, we have the boundary which exists along the polar region, which will split the warm air, which is coming from the subtropical high, feeding into the subpolar low. And the cold air, which is coming from the polar region, feeding into the subpolar low. Those two air masses will be different in terms of their properties. One is coming from a cold region. The polar easterly is very cold. It's coming from a polar region and it's very cold. These are the westerlies. They are relatively warmer. They're coming from a region of higher temperature. So those two air masses will be split along the polar front in the subpolar low pressure belt, like what we have been indicating in the previous indication or discussion. So this is our polar front. This one, it's stationary and it's permanent, it's stable. It is a fixed boundary which is splitting those two air masses. So the warm air is going in that direction and the cold air is going in that direction. They are squeezing past each other along a stationary polar front. That is the first stage. Then remember, there will be friction happening there on the boundary. The two air masses are squeezing past each other in different directions. They are ultimately going to cause a disturbance on the polar front, and the polar front is going to wave, which will lead us to stage number 2. If you now see here, this boundary is no longer straight like what it was in the first stage. is now waving or is now bending. And because of the bending of the boundary, the two air masses are now starting to circulate. The cold air is going to advance towards the warm air. And the warm air will also start to advance towards cold air, creating a circulation. That is stage number 2, which is the development stage, or what we call the wave stage. Then we go to number 3. You are seeing the difference here. This is a zone which is occupied by warm air. It's still wide when we have that disturbance on the polar front. But if we check here, the area which is occupied by the warm air is increasingly getting narrower and narrower. We have reached maturity of the weather system. The system is now strongly circulating and is now causing a displacement of warm air from the ground surface. The warm air is gradually losing its space over the ground surface, is being forced to uplift, and is now leaving the Earth's surface because of the advancement of the cold front. What we call the cold front on this side, we are saying is cold air approaching, cold air moving into a region of warm air. Then the warm front is this part here, where we have warm air advancing towards cold air. But however, there is a difference in the movement of those fronts. A cold front is much effective or is more faster compared to a warm front because cold air is denser and has got potential to push towards warm air, while its warm air is less dense and has got less potential to push towards a region of cold air, which will effectively mean that the warm sector is gradually going to get narrower and narrower because there is more cold air advancing than warm air advancing towards cold air. So this front will move faster going in that direction, the cold front. And this one will move very slow going towards this region of cold air. So ultimately, it means this space is going to get finished because the cold air will be moving faster compared to the warm air moving in that direction. So they are not able to maintain the same space because of the differences in the movement of the cold front and the warm front. So basically, that is the mature stage when the warm front has, when the cold warm sector is narrowed. Then we will go to occlusion. If we check here, stage number 4, you can see when we reach occlusion, we are saying there is a section where warm air has been completely displaced from the Earth's surface. We no longer have incidence of the existence of warm air over the Earth's surface. The warm air has been completely displaced from the Earth's surface. That is what we call the occlusion stage. So how do we show the occlusion on the weather system? If you check here, this indication here, I think you can see the differences in indications, right? This is a front, and if you see this triangular inclination, this is a cold front. And if you also check, if you see this semicircular, this is a warm front. This is a cold front. So when we have incidences of, it's the same front, there is cold, there is warm. There is cold, there is warm. This is what we call occlusion. What is the meaning of occlusion? We are saying the warm air has been completely displaced from the Earth's surface. It's now only occupying the upper atmosphere. The warm air has been displaced because of the fast movement of the cold front towards the warm sector, and it is forcing the warm air to be vertically displaced and is now only in the upper atmosphere. That is basically what we refer to as the occlusion stage, what we call the occluded stage. It will mean that the warm air has been displaced from the ground surface. We no longer have warm air close to the ground surface, but all the warm air is now in the upper atmosphere, or it has now gone to dew point and has created clouds bringing in precipitation in different forms. Right. That is the basics of our mid-latitude cyclone. Then the other thing that I also want to focus on is the two types of occlusion. There is what we call a cold front occlusion. Then we have what we call a warm occluded front. Right. If you check here, when you get a typical question, like for those ones who wrote the Gauteng preliminary paper, there was a question which was asking you to figure out the nature of occlusion on a given question. If you check on the website, you also see I typically discussed about that particular aspect of the occlusion. Right. There is what we call a warm front and a cold occluded front, and also what we call a warm occluded front. Right. The difference here is when you want to note the difference between those two fronts, check the front which is touching the ground surface. Like, what am I saying? I'm saying if we have an occlusion like this is a cross section, when you're drawing a cross section, if the question asks you to draw a cross section, remember, you just have to draw the fronts and label them. Do not put the indications. We can only use those indications of a triangle and a semicircle. We use them on an aerial view, but not on a cross section. When you're drawing a cross section, you just draw your line. We know this is a cold front. And when we have another front here, this is a warm front. A warm front is gentle, a cold front is steep. And this, if this is our ground, we are saying it's the cold front which is touching the ground here. We know this is the cold front, and this is the warm front. And the cold front is the one touching the ground, which will imply that this is a cold front occlusion. It's a cold front occlusion. It's the cold front which is touching the ground. And what is the implication here? We are saying the air which is here is very cold. And the air which is here is cooler. So we do have very cold and cool air. So typically we are saying very cold air has got potential to advance towards cooler air because of its density. It's more denser if we have very cold air on this side of the front and we have cooler air on the other side, which will mean that this front will effectively move in that direction and the warm air will be displaced vertically. So this is basically the warm sector because there's very cold air on that particular side and there's cooler air on the other side, which will mean that very cold air is going to effectively push towards the direction of a cooler air and is going to effectively push the weather system in that particular direction. Then what we call a warm front occlusion, what you can also note, like for example, that Gauteng question, there was no indication of the front here to show that which front is touching the ground. So what were you supposed to figure out was check the nature of the air on the west part of the system and check the nature of the air on the eastern part of the weather system. Also remember that the weather system is always moving in that particular direction. It will come from the west direction going to the east. So if you see very cold air on the western part, it is meaning that it is a cold front occlusion because we have very cold air which is pushing towards cooler air on the east because the weather system will be moving from the west going to the east. That is a typical mid-latitude or a temperate cyclone. And what we call a warm front occlusion, we have this situation. The cold front is here. The warm front is there. The cold front intercepts here and the ground is there. I think you can see the difference there. If this is our ground surface and we do have the warm front being over the cold front, it is implying that this is the ground. It's implying that this is a warm front occlusion. And it is the warm front which is touching the ground. If you are checking here, the warm front is this one, which is gentle, is touching the ground. And the implication also is the same. It means we have very cold air here and we have cooler air on the side. What you should note is when you are indicating the two air masses, show that they are different in terms of their temperature. If you are using cold and cool, it's fine. It shows that there is a difference in temperature. Cooler air has got relatively higher temperature compared to cold air. Or if you want to use very cold and cold, it shows a difference. Very cold, which means the temperature is very low, is relatively lower, and cool air has got slightly lower temperature. So the indication is you must take note of how you indicate the different air masses. Show that one is more colder than the other. So you cannot say it's a cool sector, it's a cold sector or a cold sector on either side because there is no distinction there in terms of the relative temperature. But if you say very cold and cold, it shows a difference. Or if you say very cold and cool, it shows a difference. So you must show that the air masses do not have the same temperature properties. They are different, though they are both in the cold sector, but the coolness is not the same. One is slightly colder than the other. If one is minus 2 degrees Celsius and the other one is 0 degrees Celsius, those two air masses are not the same. Minus 2 degrees Celsius is very cold compared to 0 degrees Celsius. If one is 5 degrees Celsius and the other one is 2, they're not the same. They are both cold, but show the extent of coldness in terms of indication of the relative coolness of the temperature. So basically that is with mid-latitude cyclones. So typical questions that you can get of a mid-latitude cyclones if you are preparing for the exams, check on the developmental stages and check on the implications of the weather system over the natural environment, over the built environment, over human activities, over economic activities. How do they affect those different aspects of life? Right. So what you need to note is you need to note that the mid-latitude cyclones, they do affect South Africa, typically in winter, and they do affect the Western Cape. That is the region which is vulnerable to that particular weather system. And you should note that their movement is they move from the west going to the east. That is why they tend to affect the Western Cape because they will be coming from the extreme west over the Atlantic Ocean, moving over to the interior. Then you note the implications. How do they affect human activities? How do they affect the environment? How do they affect the economy? And also, you should note the strategies that we can put in place to minimize the negative implications or the negative impact of such weather systems. That is what you must be prepared for. And also, typical exam questions, you must be specific. If the question is also specific, do not generalize. If the question is asking on the impact of the mid-latitude cyclones on the environment, make sure you address the environmental impacts. Do not go to other aspects which are not environmental. If the question is asking about the economy, look at the impact of the weather system on the economy of the country. Be specific if the question is also specific. And remember, if it's a paragraph question, you must give a factor and a qualifier. What are we saying? Give a direct response to the question and qualify the response. Give evidence to support or to substantiate the factor that you have given. That is a factor and qualifier. For example, the question is saying, give the effects of mid-latitude cyclones on maybe the environment. Give an impact. They will cause extreme cold conditions. It's a factor. And qualify the factor. What are the extreme cold conditions going to pose on the environment? You are now qualifying the factor. So when you are answering paragraph questions or when you are answering the 2x2 questions, you must ensure that your point is fully substantiated. It's got supporting evidence Give a direct response to the question and qualify the response by adding additional support information to what you have highlighted. That is a factor and a qualifier. That is typical of what you should do when you're answering your questions. Right. We are done with our mid-latitude cyclones. We move on to tropical cyclones. When we're looking at tropical cyclones, remember we looked at the tropical region, which is the equatorial region. We are looking at low pressure weather systems that do occur or that do happen within the tropical region. Where is our tropical region? Basically, we are saying in the tropics, we have the Tropic of Cancer, which is at 23.5 degrees to the north. And we have the Tropic of Capricorn, which typically crosses through South Africa in Limpopo, Capricorn district. It's at 23.5 degrees to the south. So we are saying the tropical region typically lies within the belt of 30 to the south and 30 to the north around the equator. So we have typical low pressure weather systems that develop in that particular region. Those are typical of what we call the tropical cyclones. Right. We want to look at them in as brief as is possible. What makes those weather systems prevail? What are the basic conditions that will favor the development of tropical cyclones? And also, maybe before we look at that, you must also note that tropical cyclones are the most destructive weather phenomenon on a global scale. They are the ones that cause the most destruction or the most loss of lives caused by such typical weather system, because they are very strong and they are very destructive. They will create very strong and gusty winds, which are very destructive. They will cause a heavy rainfall, which is also very destructive, which will cause high levels of flooding and which will result in damage to infrastructure and will result in damage to the natural environment and also loss of lives. That is typical of tropical cyclones. So what are the conditions which are necessary for their development? Right. We talked about Coriolis effect. Coriolis effect, we have what we call the relative deflective frequency. The deflective frequency differs according to latitude values. Deflective frequency of Coriolis is minimal around the equatorial region, which will mean that between 0 and 5 degrees out of the equator, Coriolis force is very minimal, is even or is almost 0% deflective frequency. But as we go towards the polar regions, as we move away from the equator, we increase in latitude, we increase our latitudinal values going towards 90. The deflective frequency will increase, which will mean that the Coriolis effect will become more prominent as we move away from the equator. So we are saying the tropical cyclones, for them to develop effectively, they need Coriolis force. They need a deflective effect, which is caused by the Earth's rotation. So basically, we are saying they do not occur within a region of 0 to 5 because the frequency of deflection is very minimal in that region. There is limited deflective frequency because the Coriolis force is not active in that region. It will act as we go towards the polar region. So it will mean that it will strengthen as we move away from the equator going towards the polar region. So basically, they need a region which is away of the 5 degrees north and south. They cannot occur effectively within the true equatorial region of 0 to 5 degrees. Then also they need a warm surface temperature, a warm ocean temperature. That is why the tropical cyclones, they typically happen over the Indian Ocean in the southern African subcontinent. Because the Indian Ocean, remember, it has a warm ocean and it has favorable temperatures for the development of the weather systems. So the basic temperature is 26.5 degrees Celsius. That is the minimum temperature required for the effective development of the weather system. And they also occur over tropical oceans. There's less friction. Yes, I think that's clear. They require a smooth surface where there's less friction. So basically, you must look at the factors which will favor the development of the weather system. That is basics of the tropical cyclone. Then we go to the features of the tropical cyclone. A tropical cyclone, basically, we're saying it's a low pressure weather system that typically affects in late summer to autumn. If the question asks you about the season of the occurrence of tropical cyclones, you must indicate that they occur in late summer. That is the relative response. Late summer, we're looking at months like end of February to March in the southern hemisphere. That is late summer. That is where we tend to have more of the tropical cyclones occurring because the temperatures will be relatively very high during those months. So it will favor the development and the effective formation of such typical weather system around that particular time. Right. Then also what you need to note is the tropical cyclones are named. They do have got particular names and they are named alphabetically. Alphabetically, we are talking of something which is common. The alphabet, we have the 26 letters of the alphabet starting from A until we go to Z. A, B, C, D, E. Which means in a particular season, if we have a tropical cyclone which has occurred, it is going to be given a name starting with A. Maybe it's named Alpha. That is the first cyclone of the season. If in that particular season, again, there is another tropical cyclone which has occurred in that particular same season, we name it with a letter B. Maybe we call it Beauty. And then another one in the same season, occurring again, we name it starting with the letter C. Maybe we call it Cindy. That is basically how we name the tropical cyclones. So typical questions that you are going to get in the examination, they will ask you how many tropical cyclones have occurred in that particular season. Remember, refer back to the season, to the alphabet. If you see maybe this tropical cyclone, maybe it's E. Maybe it's a tropical cyclone Elise. It means how many cyclones have occurred prior to this? There was A, there was B, there was C, there was D. This will be the fifth because alphabet E is the fifth on the list of alphabets. So you must take note of the names of the tropical cyclones because we know that they are typically named according to the alphabet. The first one to occur in a particular season is given a name starting A with A, second one with B, C, D, going until we got the last alphabet. But it's not possible even to get more than 10 tropical cyclones in a particular season. Maybe they might be maximum 6 or 7. Yes, ending there, maybe F, G. Yes, it's very rare for us to have a tropical cyclone with the letter M. That would be too much for a particular season. So that is basically what you should check for the exam as you prepare for the exams. And also, what you need to note is what typical weather conditions do they bring? They bring in heavy rainfall. They bring in strong and gust winds. And also they are rated according to categories of the destructive effect that they cause. Category 1, the weakest. Category 2, 3, going to category 5. They are also rated according to categories of the strength of the wind. Right. Let's go to particular aspects. We just want to touch on the key aspects in preparation of the examinations. We do not want to drill you through so much content or through new aspects that might confuse you as you go towards the exam. And also, if you check the tropical cyclones, they also do have particular different namings according to regions. We name them differently according to different geographical regions. Like, for example, if you check in Africa, we call them tropical cyclones. They are also called hurricanes in other regions. They are also called the typhoons. Hurricanes is typical of an American name. So if you see a weather system, maybe it's called Hurricane Florence, it's still a tropical cyclone. But why is it called a hurricane is because we are using a different naming in a particular different geographical region. Maybe it has affected places in America, they typically call them the hurricanes. If it's in Asia, they call them the typhoons. So those names, they must not also confuse you. It's different names for the same weather system according to different geographical spaces. But basically, we are looking at the same weather system. They are called typhoons in other regions, that is Asia. They are called the hurricanes, that is typical of American. We call them the tropical cyclones in Africa here. But basically, it's the same weather system. So the naming would depend with the region where the weather system has affected, because we do give them different names according to different geographical spaces. But basically, the naming will be in sequence of the alphabet. It's called Typhoon Alpha, Typhoon Beta, Typhoon whatever, according to the alphabet. But we should know the sequence that they are named alphabetically, but they are named also with different identities based on the different geographical spaces that we might be encountering them from. So for us here, we call them the tropical cyclones in Africa, and basically in Africa we use that common name. We do not infuse other names like the hurricanes or the typhoons. Then the stages of development, basically those are the stages of development. The initial development, the mature, then it actually decays. We rarely find questions on the developmental stages, but what I want to emphasize here is this section here. The section that is shaded on the part of this weather system. If you can check, there is this section here. And also if you check, there's this section here on all of the developmental stages. What do we call this section here? This is a particular section which is found on the southwestern extreme of the weather system. Why is it a specific section there? That one is called an active quadrant of the weather system. It's called an active quadrant. Active quadrant. How is it an active quadrant? That is the area where we have the most destructive winds. The winds are strongest in this particular part of the weather system. The winds are strongest in this particular section. That is why it's a unique section. It's usually secluded, it's shaded, and it shows that there is something happening there which is unique, which is not within the whole weather system. So this active quadrant, how does it come to exist? Our tropical cyclones, typically they move from the east going to the west, which means they will move in that direction. This is our west, this is our east. They will be coming from the east going to the west. And remember, we're also talking of Coriolis force. Coriolis force in the southern hemisphere, it causes winds to deflect to the left, which will mean that the winds, as they are circulating, they will also be deflecting to the left. So this active quadrant is a resultant effect of the combination of the movement of the weather system and Coriolis effect. That is why the winds are most destructive in this area here, because there is combined effect. The winds are being deflected, and also the weather system is also moving in that particular direction. And also the rotation of the weather system. Remember, it's a low pressure cell. We said rotation in a low pressure cell is clockwise. The winds are rotating in that direction, and there's deflective effect. So those effects, they will come to blend in this quadrant here, in this region. They are going in that direction because of Coriolis force. They are rotating in that direction. The system is moving in that direction. So the combined effect was going to create a very strong winds in that particular section of the system, creating what you call the active quadrant of the weather system, what you call that part. And what other question do you expect then? The other question that you might get, you need to note the hemisphere over which the system is actually affecting. The question might ask you about the hemisphere over which the system is occurring. We said if the system is circulating clockwise, know that it's southern hemisphere. Typical cyclones in the southern hemisphere, the rotation is clockwise. But if it's anti-clockwise, you must note that it's in the north. So if you get a typical Mapwork question or a typical practical question where you get to be asked about the hemisphere over which the cyclone is occurring, remember that whenever you see a satellite image showing clouds rotating in a clockwise direction, you know that it's in the south. If it's anti-clockwise, it means it's in the north. And also for synoptic maps, we do have different symbols which are used for the tropical cyclone. We have this symbol here, symbol like this. This is a symbol for a tropical cyclone in the southern hemisphere. It shows clockwise rotation. But if it's like this is anti-clockwise rotation. It's in the northern hemisphere. So this symbol is used for tropical cyclones. I remember this was a typical question which was asked in the term 1 test for Gauteng. They were asking about you indicating the symbol for a tropical cyclone in the southern hemisphere. Remember, the symbol is like this. It shows that the system is rotating in that direction. If it's like this. If it's like this is rotating in that direction, which means it's anti-clockwise, it's in the north. Always remember that it's clockwise in the southern hemisphere. So the system is shown by the rotor like this. Then if it's anti-clockwise, it is shown the other way around. This is clockwise, this is anti-clockwise. So also take note of those ones. If the question asks you about the hemisphere over which the system is affecting, please be mindful of how the symbols are different between the northern hemisphere tropical cyclone and the southern hemisphere tropical cyclone. Right, let's quickly go through the tropical cyclones. If you get a question asking about the impacts of tropical cyclone, maybe the question is saying discuss the impacts. Impacts, if it's not specific, positive or negative, it means you have to account for the positives and for the negatives. If it's just saying impacts on the environment, it means positive benefits of the system over the environment or negative benefits. And then what you need to note is when you are asked as referring that particular question, you should note the aspect of the weather conditions which are brought by the system. Talk about destructive effects which are caused by strong winds, or talk about effects which are caused by heavy rainfall. Because typically we know that tropical cyclone, they bring with them very heavy rainfall, which is going to cause flooding and which is going to cause destruction of infrastructure, loss of lives, loss of that is typical weather condition. And also they're going to cause very strong and gusty winds, which are going to cause also destruction. So when you're addressing the question, take note of the aspects of the weather conditions which are going to be brought by the coming of the weather system. Then you can figure out how to answer the question. So basically, this is typical of an indication of the weather system on a satellite image or on the synoptic map. Right, we move on. The cross section is like that. This is the eye of the system where there is descending air and where there are clear conditions at the middle of the weather system, and there's strong ascendance by the side of the system. We have the eye wall and we have the vortex developing here where we have vertical upliftment of the air, and we have typical of cumulonimbus clouds forming, which are tall and towering clouds created by the vertical ascent of the air as it circulates around the eye of the weather system. Right. Let's move on to the next aspect. This is tropical cyclones. This is typical second aspect of the. We're looking at traveling disturbances. Traveling disturbances associated with winter conditions and with summer conditions. Right. What we call the traveling disturbances, we are looking at typical weather systems that result that are caused by the existing pressure cells over the subtropical high region. South Africa, we say it is lying within the subtropical predominantly, and that is going to cause different weather conditions over the subcontinent of Southern Africa. We have the high pressure cell, the South Atlantic, we've talked about them. South Atlantic on the west, the Kalahari high pressure cell, and the South Indian are on the east. They do have an impact on the cold conditions which are going to be experienced over the interior, and they do affect the weather systems. That is what we call the traveling disturbances, which are typical of the subtropical and the cyclonic weather systems. Traveling disturbances in the sense that these pressure cells, what you should also note is they are not situated permanently on the same geographical space. They do have movements that they do. They move latitudinally with the shift of the ITCZ. That is the South Atlantic high pressure to the west and the South Indian high pressure to the east. When the ITCZ is further to the north, meaning to say is typical of Southern Hemisphere summer, the pressure cells will also latitudinally shift going towards the north. They will move latitudinally like that. And when it's winter, when it's typical of winter in Southern Hemisphere, they will be further to the north. Then when it's summer, it means the ITCZ is south of the equator, and they will also drift further south, so that they move latitudinally according to the shift of the ITCZ. So they are not stationary, they do move to the north and to the south according to the differences in the shift of the ITCZ, giving us differences in the seasons. Right. So in the Kalahari high pressure, so these are the two, the South Indian and the South Atlantic, are the ones that move latitudinally. But the Kalahari high pressure cell does not have the same behavior. This one, we call it a vertical displacement. It's displaced vertically. It has what we call a vertical displacement, meaning to say the high pressure cell is dominant when there's strong descending air. That is typical of winter conditions. When we have typical winter conditions, we have stable conditions over the interior. We do not have precipitation. We do not have cloud formation because there will be typical descending air. But however, it becomes weaker over summer, meaning to say the high pressure cell is now elevated, is vertically displaced, is now in the upper atmosphere, is now weaker. The descending air is no longer reaching the surface. That is how the Kalahari high pressure cell moves. It is vertically displaced. These ones are latitudinally displaced. The South Indian and the South Atlantic, they displace latitudinally according to the shift of the ITCZ. They move further to the north when it's winter in the Southern Hemisphere, because ITCZ will be in the north. Then when it's summer, the ITCZ is to the south of the equator. They will also drift southwards because of the shift of the ITCZ. But the Kalahari high pressure cell is vertically displaced. It's stronger during the winter season. There is strong descending air over the interior in winter, but however, the high pressure cell, it weakens over the summer season. So we want to look at how do they affect the weather systems over the interior of South Africa, and how do they also affect the weather conditions over the coastal regions. Quickly, a typical question that you can get, you get a question on line thunderstorms, or a question on the moisture front. It's typically one thing, the moisture front and line thunderstorms. All right, let's go directly to the moisture front and line thunderstorms. Right, before we look at that even, let's look at the impact of the Kalahari high pressure cell. We said it's stronger during winter. When you get a question which asks you about the position of the inversion layer, right, what you should note there, do not use queer terms. Refer to the inversion layer as being above the escarpment or being below the escarpment. An inversion layer, we are saying this is a layer of warm air which is trapped. Or basically, before we do look at the invasion, let's look at the concept of the invasion. The invasion is basically the reversal of the normal temperature profile of um the normal temperature profile within um the region of our the workings of the normal temperature profile. Right. We are saying we expect temperatures to be lower in the upper atmosphere. We are saying the higher you go, the cooler must it become, because the source of heat is the Earth's surface. The Earth's surface receives insolation, and it is going to cause radiation. And the more we are close to the Earth's surface, it means the temperatures are higher in the troposphere, close to the ground surface. But as we go up in the atmosphere, the temperatures must decrease. So what you call a temperature inversion, usually you get that question. The temperature inversion is the reversal now. We are going up with altitude, but the temperatures are increasing. Whenever we have a situation whereby temperatures are increasing with altitude, that is an inversion. So when you get a typical question asking about the inversion, always remember that it's a reversal of the normal temperature profile of the troposphere. We expect temperatures to drop with altitude or with height, but when we have temperatures increasing with altitude, that is now an inversion. It's not longer normal. The temperature profile must be negative. Temperatures must drop as we go into the upper atmosphere because we are moving away from the source of heat. But an inversion now, if the temperature increases with altitude, it means that is particular of a temperature inversion. So we have this inversion layer here. It's a belt of warm air which is trapped in between two cold air masses. And this inversion layer here, it is going to change its position in summer and in winter because of the effect of the Kalahari high pressure cell. Remember, we said the Kalahari high pressure cell is vertically displaced, which means it's weaker during the summer season. And if it's weaker, it means it's elevated. It's in the upper atmosphere. And this layer here is going to be also elevated. If you check the terrain here, this is our sea, and we have air which is supposed to feed over the interior here, coming from the Indian Ocean. This air will bring in moist conditions over the interior. And because there is a passage gap here, the inversion layer is elevated, it's not blocking the coming of the warm and moist air over from the Indian Ocean. The air is going to reach the escarpment, it's going to get over the interior, and it's going to reach dew point, condense, and form clouds. That is why we have typical wet conditions over the interior in summer, because there is weaker descending air. The Kalahari high pressure cell is elevated, is weaker, is vertically displaced, and is not forcing the inversion layer over the plateau. The inversion layer is well above the plateau. So you get typical questions there, which will ask you about which season is indicated. If you see a scenario like this, the inversion layer is above the escarpment, typical of summer conditions, which is going to bring wet conditions over the interior. The warm and moist air is going to feed into the interior and create wet conditions. That is typical of summer conditions. Right. Then we go to winter conditions. You see now the inversion layer is lower, it's below. When you get a question or when you get a question requiring you to describe the inversion layer, use the term the inversion layer is below the escarpment. It's below, the escarpment is here, and the inversion layer is here. Meaning to say, the inversion layer now has been forced to go down by the strong descending air of the Kalahari high pressure cell. It's stronger. This is typical of winter conditions. When it's winter, we have strong descending air, and the air which is descending is going to force the inversion layer to lower below the escarpment and block incoming warm and moist air here. That is why we have dry conditions, because the air which is supposed to feed moisture over the interior is being blocked by the inversion layer. So typical questions, they will ask you about the season. What you should not check the position of the inversion layer. If it's elevated, it's above the escarpment, it's typical of summer conditions. And what kind of weather conditions do we experience over the interior? We have moist conditions, we have rainfall, we have unstable conditions. And when it's like this one, the inversion layer is lower, is below the escarpment, it will create dry conditions and stable conditions over the interior. Warm and moist air is blocked from reaching the interior. That is typical of questions that you get on traveling disturbances associated with summer and winter conditions. Right. Let's move on to the line thunderstorms and the moisture front. Line thunderstorms, we have the South Atlantic here, we just summarize, and the South Indian. These two high pressure cells are going to feed in air into the interior. Because of anticyclonic circulation, we do have air which is being fed from the South Atlantic and air which is being also fed into the interior from the South Indian high pressure cell. And these ones are typical traveling disturbances that occur over the summer season. When we do have summer conditions, we have high amounts of rainfall occurring over the interior because of the implications which come from the South Atlantic high and the South Indian anticyclone. They feed in air over the interior, but the air that they feed over the interior will be different. Remember, over the Atlantic Ocean, we have cold conditions. It's a cold ocean, and it is going to bring in cold and dry air over the interior here, like what you are seeing. We're going to have cold and dry air being fed anticyclonically in an anti-clockwise direction. And also from here, the South Indian, because it's a warm ocean, there's a warm ocean current, is going to feed a warm and moist air. And those two air masses, remember we talked about the differences in the properties of air masses. Whenever we have two air masses of different properties, those two air masses are different in terms of their temperature and their moisture content. One is cold, the other one is warm. That is temperature. The other one is having moisture, the other one is dry. So they cannot mix. They are going to be split by a front, which is the boundary here. So this boundary is the one that we call the moisture front. Moisture front in the sense that it's going to create wet conditions. How are the wet conditions going to be realized? This air here is cold and is denser. This air here is warm and is less dense. When the two air masses meet, the cold air is going to subside and is going to force the warm air to rise. As this air rises, it reaches dew point, it creates clouds that will form rainfall. And the rainfall is going to occur in a line because the boundary will be more of a linear across South Africa. And the system moves from the west going to the east, which means the rainfall is going to be realized as the system is also going to move in that particular direction. And we have rainfall being experienced on the eastern part of the front because that is where the warm and moist air is coming from. So typical questions that you can get there, you need to note where we have high rainfall. We have high rainfall on the east because that is where warm and moist air is being fed from. It's coming from the South Indian anticyclone. And on the left side, on the western side, there is cold and dry air, which means, and also the system will be moving in air in an easterly direction. It will be moving from the west going to the east because the cold air will be pushing towards the direction of warm air, which is coming from the east. And also what you should note there, you must also note the fact that there will be line thunderstorms. Line thunderstorms are saying there will be a series of thunderstorms occurring along the moisture front. Like usually it's indicated on the synoptic map, like you will see, there will be symbols like this, and they will be in a line, indicating that we have typical thunderstorms occurring in a line. That is what we call the line thunderstorms. They will be occurring along the front. They will be occurring in a line along the front. So basically, that is what we call the traveling disturbances, which are caused by the subtropical cyclones and typical of summer disturbances. Then we also have winter conditions over the coast, what we call the backwinds. The backwinds, basically, they are caused by the descending air, which is coming from the interior, going down to the coast here, like what you are seeing. We have the strong descending air over the interior because of the Kalahari high pressure cell. The air is going to hit adiabatically and it's going to get very high temperatures as it gets to the coast, which is typical of the Berg winds, and they are going to cause hot conditions and uncomfortable conditions for people over the coastal regions because of adiabatic heating. And also what you should note is preventive measures for the berg winds. How can people prepare for them? You look at things like controlling the wildfires. There's high chance of wildfires occurring, or keeping the ground wet to avoid the spread of wildfires, or people keeping water resources to avoid dehydration, or that is basically the berg winds. I think the information is there. And then we also have typical of the coastal low pressure cells. We have the low pressure cells occurring along the coast. They move from the west going to the east along the coastal region. That is typical of the coastal low pressure cells. Right. Then we need to move on to valley climates. On valley climates, we want to focus on slope aspect, and we want to focus on the anabatic and the katabatic winds. Right. What you should note with these ones, we just want to summarize them as quick as is possible. Right. We do have what we call slope aspect. What is it that we call a slope aspect? When we're talking of slope aspect, we are looking at the orientation of the slope. We are looking at slope aspect. We are looking at orientation of the slope. What is orientation? Where is the slope facing? Right. We know well that when you're looking at slope aspect in the southern hemisphere, we have our overhead sun's position always in the north, because the sun deviates within the equatorial region, within the tropical region, 23.5 north and 23.5 south, which means here in southern hemisphere, if we have a slope which is facing towards the north, that slope is going to receive insolation during winter, and the other slope facing the opposite direction is not going to receive any insolation. That is slope aspect. We are looking at the orientation of the slope. Where is the slope facing? So in the southern hemisphere, we are saying the north-facing slopes, they are the ones that receive insolation in summer. Like, let me indicate, if this is our southern and this is our north, we are saying the sun is in the north. We are in the south here. The sun is always there. And it means the sun is going to shine over this. And it will never shine over this, because this one is facing away from the sun, but this one is facing towards the sun. This is what you call, this is what you call the zone of incidence. Zone of incidence. And this is what we call the shadow zone. So we are saying the shadow zone is always in shadow, does not receive insolation because it's facing away from the sun. And the zone of incidence is the one which is receiving insolation, is facing towards the direction of the sun. So typically we have effects on this side and also effect on the other side. Like on settlement, you tend to find that people prefer to settle on the warmer part of the slope. And also on agriculture, we have typical agricultural activities which favor the either side of the slopes. Like for example, the shadow zone, we have activities like the farming of the plantations, because they favor relatively cool conditions and also moist conditions. And also on the side, we have agricultural activities of crops that require relatively higher temperatures. So it will affect activities happening and also to affect the nature of the settlement on either side of the slope. Right, let's go to we want to focus mainly on katabatic and anabatic winds. Those are the typical questions that you can get. Right, I'll explain quickly on the anabatic and katabatic winds. Right, if we have a valley, we do have typical winds that are going to be experienced in that particular valley condition. Right, what is going to happen here? Let me illustrate. Right. Because of this situation, if we are having a valley like this, it means this is the floor of the valley and these are the valley sides. Let's say we are in the southern hemisphere, our sun is there in the north, which will also mean that the sun's rays are going to, in winter, because the sun is lower in the atmosphere, are going to only affect this. Because of slope aspect, this is what you call the north facing slope. And this is the south facing slope. So the north facing slope in the southern hemisphere is the one that receives insolation. This one here is the one which is heated directly by the sun. But this one here is in the shadow zone, is facing away from the sun. So what is going to happen here is, because of this implication of the sun's rays, which are going to hit this side, they are going to create pressure gradient. There is insolation during the day, which will mean that there will be higher temperatures. The surface is going to be heated. And remember the relationship between temperature and pressure. Whenever we have high temperature, the pressure is going to be low. So because of high temperatures caused by insolation, the pressure is going to be low pressure. And as a result, the valley floor now has got higher pressure compared to the valley side. And there's now pressure gradient. There's now high pressure in the valley floor and there's low pressure on the valley side. It's going to cause the air to blow in that direction. It's going to go up. From the floor of the valley, it's going to go up because there's low pressure there. This is typical of what we call the anabatic winds during the day, and they are typical day winds. So typical questions that you can get a question which will ask you to mention or to name the type of wind in the valley. Whenever you see an upward movement of a wind from the valley floor going to the valley side, that is typical of anabatic, and that happens during the day. Then what happens during the night? There is reversal of the movement. During the night, the valley side now becomes cold. How does it get cold? It gets cold because of long wave radiation, or what you call terrestrial radiation. There is loss of heat from the valley side during the night because of long wave radiation, and the valley side now becomes very cold compared to the valley floor. The valley floor would now be relatively warmer compared to the valley side. And now that is going to cause a low pressure developing here and a high pressure developing on the valley side. And the wind is going to reverse. It's going to go to the bottom of the valley floor. This is what we call the katabatic, which is a downslope wind. So if you get a question which asks you about mentioning the wind, remember that whenever we have a downward movement of the wind in a valley, that is typical of a katabatic, and it happens during the night. Then we also have other aspects which are very important that we must note. We need to talk about the inversion layer. We talked about that. We all look at the inversion layer in the valley. Right, the inversion layer, we're saying if there's a valley like this, and if there are katabatic winds going down, these winds are cold. They are going to displace the warm air which was in the valley, and the warm air is going to uplift. But however, the warm air is not going to be able to escape the valley because this is winter. There is strong descending air also. The Kalahari high pressure cell is causing a strong descendance, which is going now to block this air. So the air will end up in the valley, not out of the valley, but being trapped between two air masses of cold air, which is descending, and also cold air, which was katabatic, which was sinking into the valley. This is what we call the thermal belt. It's called the thermal belt. Is a band of warm air which is trapped between two cold air masses. There's cold air from the top and there's cold air from the bottom, and this warm air is trapped in between, creating a thermal belt. So typical of the valley climate, we also have thermal belts forming, and they also influence settlement. People usually want to settle along the thermal belt here because it's relatively warmer. Right, let's quickly go on. That is with the valley climate. So we also have frost pockets. Frost pockets, they form here. How do frost pockets form? Frost pockets form when dew point is below freezing point, when condensation level is below freezing point. If the air which is coming here is having moisture, and is going below the freezing point, is going to cause accumulation of frost or ice in the valley. That is typical of frost pockets. So it's typical of a question that you can also get on valley climates. So basically, you need to know the katabatic and the anabatic winds. You need to note the thermal belt. You need to note the influence of the valleys on settlement and on activities happening on settlement and of agriculture, and also the implications of frost pockets. It will also affect agricultural activities. Farmers have to grow crops which are frost tolerant if they are in a valley condition. And also the thermal belt, remember, it also affects the levels of concentrations of pollutants in the valley. Like we do have a formation of foggy conditions in the valley because of the trapping of pollutants, which will give hygroscopic nuclei of condensation in the valley during the winter season. That is why you tend to find that usually in winter in areas which are typically valley, we do have foggy conditions, which will reduce visibility and usually will cause traffic problems because of poor visibility. It's because of the pollutants which are trapped by the inversion layer. They cannot escape the valley and they will give condensation nuclei, which is going to cause misty and foggy conditions, which will reduce visibility and cause very serious traffic incidences. Right. Then with that, I think we are done with the valley climates. We need now to conclude by looking at the urban climates. The urban climates, basically, we are looking at urban areas. How do they affect? How is the climate of an urban area different from the climate of a rural area? I will touch on two aspects here. I will touch on an urban heat island, and I will also touch on a pollution dome. I think those are the two basics of urban climates. Then I think that will be fine for urban climates. Right. What you need to note here, there are two instances of urban climates. The urban climatic conditions are different from the rural climatic conditions in two dimensions, one in terms of temperature and also in terms of the level of pollutants. Right. We have what we call an urban heat island. Urban heat island. When you get a question on an urban heat island, your focus must come here to the heat part. What is heat? We're talking of temperature. And what about the temperature? We are looking at an urban area which has got a high temperature compared to the surrounding rural areas. You are done with an urban heat island. The moment you figure out that when we're talking about an urban heat island, we are worried about the temperature of an urban area being higher than that of a rural area, that is done. What causes the urban area to have high temperatures? Now you talk of the factors which promote higher temperatures in an urban area. For example, built up surfaces, for example, concrete surfaces. You talk of reflection from the buildings. You talk of the number of buildings. You talk of pollution in the urban area. You talk of but there are a lot of things which will contribute towards the urban areas having higher temperatures compared to the rural areas. That is an urban heat island. And also the implication of the heat island. How does it affect human activities? Causes dehydration, causes activities like fatigue, causes whatever is within the line of high temperatures in the urban area. That is typical of an urban heat island. How can we reduce the impact? How can we reduce urban heat islands? You now look at maybe introducing natural surfaces, introducing water bodies in the urban area, like you talk of the recreational parks in the urban area. Introducing vegetation in the urban area is going to lessen the impact of the urban heat island. That is the basics of the urban heat island. Then we go to a pollution dome. A pollution dome, we are looking at the concentration of pollutants in an urban area. Pollutants, we're looking at maybe smoke from the vehicles, smoke from industries. We are looking at those pollutants. They do concentrate in the urban area and they are going to create hazardous conditions to the urban dwellers, what you call a pollution dome. And what I want to focus on here over the pollution domes, we have two situations that you might get, maybe if you get a typical question in the examination. We have the day conditions of a pollution dome, and we have the night conditions of a pollution dome. During the day, the pollution dome takes this shape. This is our urban area, the buildings are there, and during the day, the pollution dome is elevated. The concentration of pollutants is limited. The pollutants are displaced vertically in the atmosphere. Why? Because we are having a surrounding rural area which has got cooler temperatures, and which will mean that there will be higher pressure to the outskirts of the urban area. And because of intense heating in the urban area and because of the urban heat island, is going to cause a low pressure inside the CBD. And the air is going to blow, feeding into the built up area. And there's convergence, the air is going to uplift and will diverge in the upper atmosphere. As the air is uplifting, is also displacing the pollutants. So the effect of the pollution dome is less during the day because the pollutants are displaced vertically into the atmosphere, they are plummeted and they are not concentrated. But however, at night, the effect is now felt. Like the pollution dome is now taking that shape. The buildings are there. And now, because of strong descending air, pollution domes are also typical of winter conditions because there's strong descending air during the night, and the low pressure now is no longer existent because there is no more insolation in the urban area. The level of pollutants is now concentrated here. Like the pollutants are now being forced to lower their level because of the strong descending air of the Kalahari high pressure cell, and we end up having a situation of high concentration of pollutants close to the ground surface because of the strong descending air. So the pollution dome during the day and during the night, that is typical of the night condition and typical of the day condition. So during the day, the pollution dome is elevated, is high up in the atmosphere. The pollutants are vertically displaced, they are not concentrated, but during the night, because of the impact of the strong descending air, they are now concentrated and they are now affecting human activities in the urban area. That is basically what you should note. So as you are preparing for the examinations, I urge you to be diligent, and the advice is you must attempt all the questions. Do not leave blank spaces. Attempt all questions in as much as you understand, answer the question. And also remember, if you're answering paragraph questions, follow the instruction, give the responses in paragraph format, giving a factor and also qualifying your factor. We are expecting that with geography as a subject on its own, failures must be very minimal, or we might not even talk of anyone failing to get a level 4, a level 5, because these things are practical, these things are just realistic, these things are just within our reach. We are experiencing them. Like if you talk of climate and weather, starting from the tropical cyclones, we talk to mid-latitude cyclones, they are actually practical, it's a living subject. So in as much as you understand the geographical aspect of what happens in your day-to-day life, apply them in the examination, and it must be 100% pass for geography across the whole of South Africa. And it has been like that, or it must maintain that standard. So we hope that this discussion is going to actually benefit you in some dimension, and is also going to assist you in whatever you will encounter in the examination. And the other thing is confidence. Be very confident of yourself. When you get to Mapwork calculations, can you please be very accurate with your calculations? Try to be accurate with your measurements. Try to be accurate with your calculations. When it's a payment of bearing, can you please use your protractor precisely and get the correct bearing, get the correct measurement, get the correct calculation and everything must be in position. It is my belief that 2024 is your year. In geography, I believe everyone must be attaining 100% pass as a subject, and also as an individual, I urge you to attain the best of your level. The world has more to offer that is waiting for you. I thank you for being with the discussion. Your host, Conrad Mpinguri. Thank you.